Imagine you're an astronaut. The familiar hum of your ship is a distant memory, now replaced by an impossible, perfect silence. Your tether snapped. You're drifting, slowly at first, toward a perfect circle of absolute darkness. It's a hole punched in the very fabric of the cosmos, swallowing the starlight behind it. This isn't just empty space, it's a destination. You are approaching the edge of a black hole, a line in spacetime they call the event horizon. You are about to cross the point of no return. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. What will you see? What will you feel? And why is this journey so strictly a one-way trip? This is the story of your final moments, a slow, deliberate fall into the universe's most profound mystery. This is why the laws of physics, as we know them, have already sealed your fate. Stay with us as we unpack the journey from which there is no escape. The invisible giant. Before your journey takes you any closer to that silent, gaping maw, let's just pause. To understand why you can't come back, we first need to get a handle on what you're falling towards. A black hole isn't really a hole in the way you might imagine. It's not empty. In fact, it's the exact opposite of empty. It's a mind-boggling concentration of matter packed into a space so tiny, it defies all logic. Think about our sun, a star so vast you could fit over 1,000,000 Earths inside it, and imagine crushing it down. Not to the size of a city, or even a house, but to the size of a small town. Now, picture something even bigger, a star 20 times more massive than our sun, collapsing under its own weight into a space no larger than a single mountain. What you get is an object with a gravitational pull so ferocious, so overwhelmingly powerful, that it becomes a prison for everything that gets too close, including light itself. That's the essence of a black hole. But how can gravity, a force we deal with every day, become that dominant? The answer lies in one of the most beautiful and revolutionary ideas in all of science, Albert Einstein's theory of general relativity. Back in 1915, Einstein totally reshaped our understanding of gravity. He figured gravity isn't a force, in the usual sense, like a push or a magnetic pull. Instead, gravity is what happens when mass and energy warp the very fabric of the universe, a four-dimensional canvas he called spacetime. The classic way to picture this is with a trampoline. Imagine a flat, taut trampoline sheet. That's spacetime when it's undisturbed. If you roll a little marble across it, it travels in a perfectly straight line. But now, place a heavy bowling ball in the center. The sheet sags, creating a deep well. If you roll that same marble again, it no longer goes in a straight line. It curves, spiraling down into the dent made by the bowling ball. It's not being pulled by some mysterious force, it's simply following the curve in the fabric it's traveling on. That's exactly what gravity is. The Earth isn't pulling you down, it's warping the spacetime around it, and you're just caught in that curve. The moon doesn't orbit the Earth because of some invisible leash, it's continually falling along the curved path of spacetime our planet has created. A black hole is this idea taken to its most terrifying extreme. It's not just a bowling ball on a trampoline, it's a weight so immense that it has punched a hole clean through the fabric. The curvature of spacetime near a black hole is so profound that all paths for every piece of matter and every ray of light bend inward. Once you get close enough, every single possible direction you could move points toward the center. Escaping wouldn't just take a fast ship, it would mean traveling backward through space, which is impossible. You're caught in a current of spacetime itself, a current that only flows one way, down. Birth of a monster. So where do these cosmic monsters even come from? They aren't just born, They're forged in the most violent and spectacular events the universe has to offer, the death of giant stars. Throughout its life, a star is a battlefield. Two colossal forces are locked in a constant, titanic struggle. First, there's gravity, the relentless inward crush of the star's own enormous mass, always trying to pull everything together into a single point. Fighting against it is the outward pressure from nuclear fusion blazing away in the star's core. Deep inside, under unimaginable heat and pressure, hydrogen atoms are slammed together to make helium, releasing a tremendous flood of energy. This energy pushes outward, perfectly balancing gravity's inward pull. It's this delicate balance that lets a star like our Sun shine steadily for billions of years. But this balance can't last forever. Eventually, the star runs out of fuel. For a star around the size of our Sun, the end is pretty gentle. It will swell up into a red giant, puff away its outer layers, and leave behind a dense, cooling core called a white dwarf. But for the true giants of the cosmos, stars at least 8 to 20 times the mass of our Sun, the end is anything but gentle. When a massive star burns through its main fuel, it starts fusing heavier and heavier elements, helium into carbon, carbon into neon, and so on, all the way up to iron. Iron is a dead end. Fusing iron doesn't release energy, it consumes it. All of a sudden, the outward push from fusion just stops. The battle is over. Gravity wins. And it wins catastrophically. In a fraction of a second, the star's core, which might be bigger than our entire planet, collapses under its own stupendous weight. This collapse happens unbelievably fast at nearly a quarter of the speed of light and triggers a massive shockwave. The outer layers of the star are blasted into space in a cataclysmic explosion we call a supernova. For a few weeks, this single dying star can outshine its entire galaxy, one final, glorious burst of light. But what about the core left behind? If the original star was massive enough, the collapsed core will be so dense that no known force in the universe can stop it from collapsing further. It crushes itself past the density of a white dwarf, past the density of a neutron star, and just keeps going. It collapses until it forms an object with basically zero volume and infinite density. It forms a gravitational singularity. A black hole is born. These are called stellar mass black holes, and they can be anywhere from a few times the mass of our Sun up to a few dozen. But there's another, more terrifying class of black hole out there, the supermassive black hole. These behemoths lurk in the hearts of most large galaxies, including our own Milky Way. The one at the center of our galaxy, Sagittarius A*, has a mass of about 4 million suns. Others in distant galaxies can be billions of times the mass of the Sun. One of the most massive ever observed, Ton 618, has a mass estimated to be as high as 66 billion times that of our Sun. The origin of these giants is one of the great unsolved puzzles in cosmology. Did they form from the collapse of the very first, truly gargantuan stars? Or did they grow over billions of years by gobbling up smaller black holes and stars? Recent discoveries, thanks to telescopes like the James Webb Space Telescope, have found surprisingly massive black holes in the very early universe. This challenges our models, suggesting that whatever the process is, it can happen much faster than we used to think. Regardless of how they got there, their existence is undeniable, and their influence on the galaxies they call home is profound. Seeing the unseeable. Now, here's a fundamental problem with studying black holes. It's right there in the name. They're black. They don't give off any light, and any light that falls in is gone forever. So, how do we know they're even there? How do you find something that is, by its very nature, invisible? Well, you don't look for the black hole itself, you look for the chaos it creates around it. A black hole is like an invisible dancer in a crowded room. You can't see the dancer, but you can see the people they shove aside, the drinks they spill, and the clear path they carve through the crowd. Astronomers are masters at spotting this kind of cosmic disruption. One of the most spectacular ways we find them is by watching them eat. While they don't suck things in like a cosmic vacuum cleaner, their powerful gravity can capture nearby gas and dust. This material doesn't just fall straight in. Instead, it gets pulled into orbit, forming a vast, flat, spinning structure called an accretion disk. As the matter in this disk spirals closer and closer to the event horizon, it gets squeezed and heated to millions of degrees by friction and intense gravitational forces. This superheated material glows brilliantly, not just in visible light, but across the entire electromagnetic spectrum, especially in X-rays. For some supermassive black holes, these accretion disks can get so bright they outshine all the billions of stars in their host galaxy combined. We call these incredibly bright galactic cores quasars, and they are some of the brightest objects in the universe, visible from billions of light years away. They're cosmic lighthouses, powered by a feeding black hole. Another powerful method is just to watch the stars. For decades, astronomers pointed their telescopes at the center of our Milky Way and tracked the movements of a small group of stars. These stars were whipping around a seemingly empty point in space at incredible speeds, some reaching several percent of the speed of light. Their orbits were tight, fast, and perfectly followed the laws of motion. The only possible explanation was that they were orbiting an unseen, incredibly massive, and compact object. By precisely measuring these orbits, astronomers calculated the object's mass, about 4 million times that of our Sun, all packed into a region smaller than our solar system. This was the smoking gun for Sagittarius A*, our galaxy's central supermassive black hole, a discovery so important it won the Nobel Prize in Physics in 2020. And in this century, a revolutionary new window to the universe opened up: gravitational waves. Just as Einstein predicted, when massive objects like black holes slam into each other, they create ripples in the fabric of spacetime, like a boat moving through water. These ripples are unbelievably tiny. By the time they reach Earth from a distant galaxy, they stretch and squeeze the space around us by an amount thousands of times smaller than the nucleus of an atom. Yet, with hypersensitive instruments like LIGO, we can now hear these waves. Since the first detection in 2015, we've heard the gravitational sound of dozens of black hole mergers. We can listen to the final, frantic chirps as two black holes spiral into each other and combine, an event that, for a moment, can release more energy than all the stars in the observable universe combined. And finally, the most direct evidence of all. By linking radio telescopes across the globe to create a virtual, Earth-sized observatory called the Event Horizon Telescope, EHT, astronomers did the impossible. They took a picture of a black hole. Or, more accurately, they photographed its shadow. The now famous images of M87* and our own Sagittarius A* show a dark central region, the area from which no light can escape, silhouetted against the glowing, lopsided ring of superheated gas swirling around it. We are seeing, for the first time, the edge of the abyss. The point of no return. The point of no return. The event horizon. This brings us back to you, the astronaut, drifting ever closer to that perfect circle of darkness. That boundary is the event horizon, and it's the most important feature of a black hole. It's not a physical surface you could touch. There's no signpost, no gate, not even a change in the texture of space. As you cross it, nothing special would seem to happen at all. You just glide across this invisible line, totally unaware that you've just made the most final crossing of your life. So why is it the point of no return? To get this, let's go back to that idea of space-time as a flowing river. Imagine you're in a canoe on a wide, calm river. You can paddle any way you want, upstream, downstream, over to the bank. Let's say your top paddling speed is 5 miles per hour. As long as the river's current is slower than 5 miles per hour, you're free. You can always turn around and paddle back. But now, the river narrows and starts to pick up speed. The current hits 3 miles per hour, then 4. It's getting tougher to go upstream, but you can still do it. Then, you reach a point where the river's current is flowing at exactly 5 miles per hour. Right on that line, if you paddle as hard as you can directly upstream, all you can do is stay in one place. You're fighting the current to a standstill. What happens if you drift just 1 foot past that line? The river's current is now 1 mile per hour. Your max speed is still 5. No matter how hard you struggle, no matter which way you point your canoe, you are going downstream. You have crossed the point of no return. This is the best analogy for a black hole's event horizon. Spacetime itself is flowing into the black hole. Far away, the current is slow. But as you get closer, it speeds up. The event horizon is the exact spot where the inward flow of spacetime becomes faster than the speed of light. Since Einstein taught us that nothing can travel through space faster than light, once you're over the horizon, escape is impossible. It's not about having a more powerful rocket. It's like a fish caught in a waterfall. The fish can swim, but if the water itself is falling faster than the fish can swim, the fish is going down. You are now inside a piece of space-time that is falling into the center faster than light. Every single direction you could possibly move now leads, inevitably, inward. This leads to one of the weirdest consequences in all of physics, the dual perspective. What happens to you is radically different from what an observer, say, your mission commander watching from a safe distance, sees. From your perspective, things feel normal. Your watch ticks at 1 second per second. The universe ahead still looks mostly the same. But for your commander, something very strange is happening. As you fall deeper into the gravity well, the light reflecting off your spacesuit has to fight its way out. This climb robs the light waves of energy, stretching them out and shifting them toward the red end of the spectrum. It's called gravitational redshift. Through the commander's telescope, your image would turn red, then deep red, then fade into infrared, and finally into undetectable radio waves. At the same time, they'd see an extreme form of time dilation. The intense gravity would make your time slow down relative to theirs. They'd see your movements become agonizingly slow. The final wave of your hand would seem to take minutes, then hours, then centuries. Your image would appear to freeze right at the edge of the event horizon, never actually crossing it. From the outside, it takes an infinite amount of time for you to fall in. Your image is plastered on the event horizon for eternity, fading into nothing. But for you? There's no freezing, no pause. You cross the event horizon in a finite amount of your own time and continue your journey into the darkness. Both perspectives are real. Both are correct in their own frame of reference. This is the profound weirdness of relativity. The journey inward. You've crossed the line.
You're now invisible to the rest of the universe, which only sees your frozen, fading ghost on the horizon. Your journey continues into the black hole. So, what happens now? Here, the very roles of space and time begin to warp and switch. Outside the black hole, you have freedom to move in space forward, backward, left, right. But your movement in time is fixed. You are always pushed forward into the future. Inside the event horizon, that reality flips. Your fate in space is now sealed. There is only one direction you can go, forward, toward the singularity at the center. Trying to move away from it would be like trying to travel back in time. It's impossible. The future is no longer a asterisk when, it is a asterisk where asterisk, the singularity. All paths, all possible futures, end at that one point. As you're pulled toward this fate, you would start to experience one of the most gruesomely named effects in astrophysics, spaghettification. This is caused by tidal forces, basically, the difference in gravitational pull over a distance. On Earth, the Moon's gravity pulls a little more on the side of the planet closest to it, causing our tides. The difference across your body is tiny. Near a black hole, though, the gravitational gradient is astoundingly steep. Assuming you're falling in feet first, the pull on your feet will become exponentially stronger than the pull on your head. You will be stretched, elongated, like a piece of spaghetti. At the same time, since gravity is pulling everything toward the central point, your shoulders would be squeezed inward. You'd be stretched vertically and compressed horizontally, drawn out into a long, thin stream of atoms before being torn apart. Interestingly, whether this happens before or after you cross the event horizon depends on the size of the black hole. For a small, stellar mass black hole, the tidal forces are insane even outside the horizon. You'd be ripped to shreds before you even got to the point of no return. But for a supermassive black hole, it's a different story. Because its mass is so much greater, its event horizon is enormous, potentially bigger than our solar system. The gravitational gradient at this distant horizon is actually quite gentle. The difference in pull between your head and your feet would be unnoticeable. You could sail across the event horizon of a supermassive black hole without feeling a thing, completely unaware of the tidal forces waiting for you much, much deeper inside. Your peaceful passage is temporary, of course. As you continue your fall toward the center, the tidal forces would inevitably grow to infinite strength, and spaghettification would be your ultimate end. The end of the line, the singularity. All paths inside a black hole lead to one place. The final destination. The heart of the abyss. The singularity. What is the singularity? According to Einstein's general relativity, it's the center of the black hole, a point where all of its mass has collapsed into a region of zero volume. That means its density is infinite. The curvature of spacetime is infinite. The tidal forces are infinite. At the singularity, the beautiful equations that have described your journey so far just break. The laws of physics as we understand them stop working. It is, in the truest sense, the end of spacetime itself. It's not really a place in our universe, it's a boundary where the universe itself ceases to exist. Anything that reaches the singularity is crushed out of existence, its matter added to the black hole's mass, but its form and information lost forever. Now, this is what our current theories tell us, but we know they're incomplete. General relativity is brilliant, but it doesn't include quantum mechanics. The singularity is where these two great pillars of modern physics collide head-on. To really understand what happens at the center of a black hole, we'd need a theory of quantum gravity, a theory of everything that we just don't have yet. Maybe it isn't a point of infinite density. Perhaps it's some exotic state of matter, a fuzzball of strings, or a Planck star, where the collapse is finally halted by some kind of quantum pressure. But for now, we simply don't know. The singularity remains hidden, protected behind the one-way door of the event horizon, a concept called the cosmic censorship hypothesis. Our journey, which began with a silent drift through space, ends here. You have been stretched, torn apart, and finally crushed into a point where space and time no longer have meaning. Your mass is added to the black hole, making its event horizon just a tiny bit larger, ready for the next traveler. You've become one with the ultimate enigma. The mysteries of black holes push our understanding of physics and our imaginations to the absolute limit. If this journey into the abyss has captivated you and you want to explore more of the universe's most profound secrets, make sure you subscribe and ring that notification bell. And let us know in the comments, what cosmic mystery fascinates you the most? From the gentle curve of space-time to the violent death of a star, from the invisible line of the event horizon to the mind-shattering idea of the singularity, the story of a black hole is the story of gravity's ultimate triumph. Escaping one is impossible, not because of some wall in your way, but because space and time themselves conspire to ensure there is no way out. The very fabric of reality becomes a one-way street. Your final journey as our astronaut was a slow descent into the unknown, governed by the elegant but unforgiving laws of Einstein's universe. While you may have crossed the horizon in an instant, your ghost, an image of you frozen in time, forever red-shifting into nothingness, remains as a testament to your journey for the rest of us to see. It's a powerful reminder that out there, in the silent darkness between the stars, there are places where the rules of our everyday reality are rendered utterly meaningless, leaving behind only a lingering sense of awe. Part 2. How black holes are born. Before something becomes a black hole, it begins as something almost comforting. A star. Not a hole. Not a monster. Not a cosmic trap waiting in the dark. Just a star, shining quietly across space, doing what stars do for millions or even billions of years. If you were far away, you would never guess that one day this bright, steady object could become one of the most unforgiving places in the universe. And maybe that is part of what makes black holes so fascinating. They are not born strange. They become strange. To understand why escaping a black hole is impossible, we first have to understand how such an object comes into existence at all. Because a black hole is not magic. It is not a break in the rules. It is what happens when the rules of nature are followed all the way to one of their most extreme endings. So for a little while, let's step away from the event horizon. Let's move backward in time, long before the darkness, long before the silence, long before the point of no return. Let's go back to the life of a giant star, still burning, still resisting collapse, still holding itself together against the oldest and most patient force in the cosmos: gravity. Every star lives inside a kind of tension. On one side, there is gravity, always pulling inward, always trying to gather everything into a smaller and smaller space. On the other side, there is pressure from the star's core, created by nuclear fusion. That pressure pushes outward. As long as those two forces remain in balance, the star survives. That balance is the quiet secret behind starlight. When we look at a star in the night sky, we often imagine something serene, something almost eternal. But inside a star, nothing is calm. Deep in its core, unimaginable pressure crushes hydrogen atoms together until they fuse. In that fusion, a tiny bit of mass is turned into energy. And that energy pushes outward with extraordinary force. So a star is not resting. A star is holding itself together through conflict. Gravity says, come inward. Fusion says, not yet. And for most of a star's life, that argument never truly ends. It simply continues, second after second, year after year, age after age, with astonishing precision. The star survives because neither side fully wins. Our own sun lives this way. Right now, as you listen, the sun is not just shining. It is negotiating with gravity. It has been doing that for about 4-6 billion years, and it will continue for billions more. But the sun, important as it is to us, will never become a black hole. That is one of the first calming facts worth holding on to. Black holes are not what all stars become. Only the truly massive ones go down that road. That detail matters. Because size changes fate. A smaller star can die gently, at least by cosmic standards. It may swell, shed its outer layers, and leave behind a white dwarf. Dense, yes. Strange, yes. But not a black hole. A much larger star, though, lives a more dramatic life and dies a far more violent death. And this is where the story begins to darken. A massive star burns hotter than a smaller one. It shines more fiercely, but that brilliance comes with a cost. It spends its fuel faster. Much faster. In a sense, the biggest stars live the shortest lives. They burn with such intensity that they race through the stages of their existence. That may feel a little familiar. In nature, great intensity often means great instability. A candle can burn for hours. A fire fed by dry wood and wind can consume everything in minutes. Massive stars are like that. They are powerful, but power is not the same as permanence. At first, the star fuses hydrogen into helium. That is the long, stable chapter. But when hydrogen in the core begins to run low, the balance changes. Gravity presses harder. The core contracts. Temperatures rise. And that rising heat allows the star to begin fusing heavier elements. Helium becomes carbon. Carbon can lead to neon. Neon to oxygen. Oxygen to silicon. Step by step, the star begins building a layered interior, almost like an onion made of fire. Different shells deep inside the star fuse different elements. Each layer is hotter, denser, and more intense than the last. For a while, this works. For a while, the star keeps finding new ways to resist collapse. But there is a limit, and that limit is iron. Iron is where the story changes. Up until that point, fusion gives energy back to the star. It helps hold gravity off. It keeps the outward pressure alive. But iron is different. Iron does not reward the star for fusing it. Instead of releasing energy, iron fusion takes energy in. It is a dead end, a quiet wall. A star can burn hydrogen and live. It can burn helium and continue. It can move through heavier and heavier elements, though each stage becomes shorter than the one before. But when the core becomes rich in iron, the star has reached the end of the road. It has no more profitable fuel left. And once that happens, gravity finally sees its chance. Imagine a vast cathedral whose pillars have been holding up the roof for ages. Then, in a moment, those pillars lose their strength. The roof does not politely lower itself. It crashes. That is closer to what happens inside a massive dying star. The outward support weakens. Gravity rushes in. The core collapses with terrifying speed. What had been held apart for millions of years suddenly falls inward in a fraction of a second. And when I say collapses, I do not mean a slow sinking. I mean a catastrophic implosion. The core, once enormous, is crushed smaller and smaller under its own weight. Electrons are forced into protons. Matter is compressed to extremes that are almost hard to picture. The densities become so high that the ordinary language of everyday objects stops helping very much. We are no longer talking about solid, liquid, or gas. We are talking about matter pushed into a realm where familiar intuitions fail. Outside the collapsing core, the rest of the star has not yet understood what has happened. The outer layers are still falling inward. Then suddenly, the crushed core resists further compression for a brief moment, and a shock wave surges outward. The result is one of the most spectacular events in the universe: a supernova. For a short time, a single dying star can outshine an entire galaxy of ordinary stars. It can release more energy in moments than our sun will radiate across its whole lifetime. Elements forged in that explosion are scattered into space. Much of the calcium in your bones, the iron in your blood, the oxygen you breathe, all of it has roots in ancient stars that died before the sun was born. That is another beautiful thing about this story. Black holes are born from destruction, yes. But that destruction also seeds the universe with the raw material for planets, oceans, atmospheres, and living bodies. Death and creation are not as separate as they seem. Still, not every supernova leaves a black hole behind. Sometimes the collapsed core becomes a neutron star instead. Neutron stars are extraordinary objects in their own right. They can pack more mass than the sun into a sphere not much wider than a city. A teaspoon of neutron star matter would weigh more than a mountain on Earth. They spin rapidly. They can produce beams of radiation. Some are among the strangest known objects in the cosmos. But even a neutron star has a limit. If the leftover core after the explosion is too massive, not even neutron pressure can hold it up. There is no stable state left. No further compromise. No new balance to be found. Collapse continues. And this is the moment a black hole is born. Not because something mystical appeared. Not because the universe broke. But because gravity won completely. That is what a black hole really is at its beginning. The final victory of inward collapse. A place where so much mass has been squeezed into so little space that the structure of spacetime itself is forced into an extreme form. It is worth pausing there, because one of the easiest mistakes to make is imagining a black hole as some kind of hungry cosmic vacuum cleaner, floating through space and swallowing everything nearby. But that picture is not quite right. A black hole forms from matter that was already there. It is not an empty mouth. It is the remains of something that once shone. A star lived. A star burned. A star ran out of options. And then gravity finished the story. That alone already changes the emotional feeling of a black hole a little. It stops being just a monster in the dark and becomes, instead, the final chapter of a life cycle. A severe chapter, yes, but still part of a pattern the universe repeats. And yet, black holes do not all come from one single path. The ones formed from collapsing stars are what we call stellar mass black holes. They may contain several times the mass of our Sun, or much more. But elsewhere in the universe, especially at the centers of galaxies, there are black holes that are vastly larger. Supermassive black holes. These are not just 10 times or 100 times the Sun's mass. Some are millions or even billions of times more massive than the Sun. Our own galaxy, the Milky Way, has one at its center. We call it Sagittarius A star, though despite the name, it is not a star at all. It is a supermassive black hole, sitting in the galactic core, surrounded by stars that orbit it under its enormous gravitational influence. How do these giants form? That is one of the great unfinished questions in astronomy. We have good ideas, but not a final answer. Perhaps some began from the collapse of enormous early stars, then grew by feeding on gas, dust, and smaller stars. Perhaps some formed from direct collapse, where huge clouds of matter in the early universe fell inward before ever becoming ordinary stars. Perhaps smaller black holes merged again and again over vast stretches of time, building the giants we see now. The universe is not obligated to reveal every step of its history in perfect clarity. Sometimes science gives us solid ground. Sometimes it gives us a shoreline with fog beyond it. This is one of those foggier places. But even there, we know enough to say something important. Black holes are not rare little accidents. They seem to be woven into the architecture of the universe. They appear in different sizes, through different paths, and they influence the structure around them in profound ways. In some galaxies, the central black hole helps shape the galaxy itself. The relationship is still being studied, but the pattern appears again and again. A galaxy grows. A black hole sits at its heart. Matter swirls, stars orbit, energy erupts from near the center in extraordinary jets, and the cosmic city organizes itself around an invisible ruler. It is one of those strange facts that feels almost poetic. At the center of so many galaxies, there is darkness. Not because nothing is there, but because too much is. Now, if you picture the birth of a black hole, you might imagine a sudden moment where a star vanishes and a clean, silent hole appears in its place. But reality is more turbulent than that. The formation is violent. Matter moves at extraordinary speeds. Temperatures rise. Shock waves tear through the star. Radiation floods outward. And if enough material remains nearby afterward, some of it may spiral around the newborn black hole, heating up and glowing brilliantly as it falls in. So the birth of a black hole is not always dark at first. Sometimes it is surrounded by some of the brightest events in the universe. That contrast is part of the beauty here. A black hole itself does not shine, but the process of becoming one can fill space with light. It is as if the universe insists on one final blaze before silence. And maybe that helps us understand something deeper. The black hole is not the opposite of the star that came before it. It is the consequence of that star's life. Everything that made the star powerful, its mass, its heat, its intensity, also helped determine the severity of its end. A small, stable life leads to one fate. A massive, furious one leads to another. In that sense, the black hole is not separate from the star. It is the star's final form. And once that final form exists, space around it is never the same again. Because here is the crucial point. When so much mass collapses into so little volume, gravity does more than pull hard. It reshapes the geometry around the object. The paths that matter and light can take become more and more limited. The deeper you go, the less freedom remains. And eventually, if the collapse is extreme enough, a boundary appears. The event horizon. That is the line we are moving toward throughout this journey. The invisible threshold where return stops being possible. The place where, too late, becomes a physical fact. But before we get there, there is one idea we still need to build carefully. Why does gravity become so overwhelming in the first place? Why can a star collapse into something that not even light can escape? To answer that, we need to slow down and talk about a simpler concept first. A concept that begins not with black holes, but with something much easier to picture. What it means to escape gravity at all. Before we move on, though, let's just sit with this image for a moment. Somewhere in the universe, a massive star spends millions of years resisting its own collapse. It glows. It burns. It holds itself together through a delicate war between pressure and gravity. Then one day, the fuel runs low. The core changes. Iron appears. Support fails. The star implodes. The outer layers explode outward in brilliance. And at the heart of all that violence, something remains. Not a star anymore. Not a planet. Not a cloud. A black hole. A region where gravity has become so severe that the future of anything nearby begins to bend inward. If these slow journeys through the universe help you rest a little more deeply, you can leave a like, subscribe, or simply stay with the story. And if you feel like sharing, I'd love to know in the comments what cosmic object unsettles you the most: black holes, neutron stars, quasars, or something even stranger. For now, though, we are only at the beginning. The black hole exists. It has been born. And the next question is the one that brings us even closer to the heart of the mystery. What, exactly, does it take to get away from gravity? And what does it mean when the answer becomes more speed than the universe allows? Part 3. What it means to escape gravity. Imagine standing on a quiet hill just after sunset. The air is still. The ground beneath your feet feels solid and familiar. You pick up a small stone and toss it gently into the air. For a brief moment, it rises, almost confidently, as if it might keep going. But then it slows, hesitates, and falls back down into the grass. You throw another one, harder this time. It rises higher, stays up a little longer, and then returns again. No matter how many times you try, unless you throw it with enough speed, the story stays the same. Upward for a moment, then back down. The earth always seems to call it home. That simple little motion, a stone going up and then falling back, turns out to be one of the gentlest ways to begin understanding why a black hole cannot be escaped. Because before we can talk about the most extreme gravity in the universe, we need to talk about ordinary gravity. The kind we live with every day. The kind so familiar that we almost stop noticing it. Gravity is quiet like that. It does not announce itself with noise. It does not flash or glow. It simply waits, patient and constant, shaping everything from the fall of a leaf to the orbit of a planet. And one of the most important questions you can ask about gravity is this: what does it actually take to get away from it? Not to jump for a second. Not to drift for a while. Not to rise and then fall back. But to truly leave. To escape so completely that you never return unless something else stops you. That is where the idea of escape velocity begins. Escape velocity sounds technical at first, but the idea behind it is beautifully simple. Every object with mass has gravity. If that object is large enough, and you are close enough to it, there is a certain speed you would need in order to break free from its pull without needing more thrust afterward. If you start with that speed, or more than that speed, you escape. If you start with less, gravity will eventually win and pull you back. That is all escape velocity means. It is the speed needed to leave a gravitational grip for good. On Earth, that speed is very high. Around 11.2 kilometers per second, or about 25,000 miles per hour. That number can sound almost absurd when you first hear it. It is far faster than a rifle bullet, far faster than a jet, faster than anything in ordinary human experience. It is the reason rockets need such enormous power just to leave our planet. And yet, even that enormous speed is nothing compared with the cosmic speeds we are about to meet. Still, Earth is the right place to begin, because Earth teaches the principle in a way the body can almost feel. When you jump, you do not escape Earth because your speed is nowhere near enough. Your body rises for a moment because you gave yourself some upward motion, but gravity steadily drains that motion away. You slow down, stop at the top, and come back. A ball thrown into the air does the same. An arrow does the same. Even the tallest mountain ever climbed still sits deep inside Earth's gravitational hold. To escape, you do not just need direction. You need enough speed that gravity can never quite pull you all the way back. That alone is already a useful shift in thinking. Because many people casually imagine gravity as if it were some kind of invisible hand, always grabbing and pulling objects downward. But a better way to think of it, at least for this purpose, is as a debt of motion. If you want to leave a world behind, you must begin with enough speed to pay that debt in full. If you do not, gravity slowly takes your motion away until you turn around. On a small asteroid, the debt is tiny. A person with a strong jump might almost leave the surface. On the Moon, the debt is larger, but still modest compared with Earth. The Moon's escape velocity is only about 2.4 kilometers per second. That is why lunar missions were difficult, but not as punishing as launching from Earth. The Moon's pull is gentler. Its grip is looser. On Jupiter, the debt becomes much larger. On the Sun, larger still. And that is the pattern we need to keep following. Bigger mass and greater compactness mean stronger gravity. Stronger gravity means a higher escape velocity. The more severe the gravitational well, the faster you must move to climb out of it. That phrase, gravitational well, is worth lingering on for a moment. Imagine a landscape of valleys and hills. A ball placed in a shallow dip can be rolled out with very little effort. But a ball placed in a deep well requires much more speed to climb back up. The deeper the well, the harder it is to escape. Planets create wells. Stars create deeper wells. Black holes create wells so extreme that the very idea of climbing out begins to fail. But we are not there yet. For now, it helps to stay with simpler worlds. Suppose Earth were somehow compressed into a smaller and smaller size while keeping the same mass. The planet would not become heavier in total, but its gravity at the surface would become stronger, because all that mass would be packed into a tighter region. If you stood on that compressed Earth, the escape velocity from its surface would rise. Shrink it enough, and the required speed becomes greater and greater. This is a deeply important point. A black hole is not terrifying just because it is massive. Plenty of things in the universe are massive. What makes a black hole special is that its mass is concentrated into such a small region that the escape velocity near it becomes extraordinary. That is where the story begins turning from difficult to impossible. But before we reach that word, impossible, let us stay one more moment with the ordinary logic of escape. If you ride a bicycle up a hill, you feel resistance. The hill takes energy from you. If you do not pedal hard enough, you slow down and stop. Gravity has not become dramatic. It has just quietly won. When a rocket launches from Earth, the same basic struggle is happening, only on a much larger scale. The rocket is not merely trying to go upward. It is trying to gain enough speed that Earth's gravity cannot reclaim it. And that is why rockets do not just rise. They accelerate ferociously. They burn fuel in enormous quantities. They shed stages to become lighter. They do everything possible to buy speed, because speed is freedom. Without enough of it, there is no leaving. In fact, even objects that seem to be escaping are often only borrowing time. A rocket launched straight upward without enough speed will go high, perhaps very high, but eventually it will slow and fall back. It will have climbed the hill, but not enough. Only when the speed crosses the threshold does the story truly change. This threshold nature is what makes escape velocity so powerful as an idea. It is not a vague gradient. It is not just, more is better. There is a dividing line. Below it, return is inevitable. Above it, escape becomes possible. That kind of threshold feels almost philosophical. There are moments in life like that too. A door closes. A bridge burns. A decision carries you beyond return. Before that line, reversal is possible. After it, the future changes shape. Physics has thresholds like that, and the event horizon of a black hole is the most severe one of all. But let us not rush there. There is another quiet misconception that needs clearing away first. When people hear escape velocity, they sometimes imagine that you must keep moving at that speed forever. But that is not quite right. If there were no air, no engines, and no other complications, escape velocity is the speed you need at the start. Gravity will keep slowing you down as you move away, but if you began with enough speed, it can never reduce your motion all the way to zero before you are effectively free. So escape velocity is not the speed you maintain. It is the speed that changes your fate. That distinction matters more than it may seem. Because when we eventually say that a black hole's escape velocity exceeds the speed of light, we are not saying you would need to cruise forever at some impossible speed. We are saying that to get out at all, even in principle, you would need an initial advantage greater than the universe permits. And once physics says no even in principle, the conversation changes. That is when difficult becomes final. Now, the speed of light has a special role in modern physics. It is not just the speed at which light happens to move. It is built into the structure of reality. According to relativity, it is the ultimate speed limit for anything carrying information, matter, or influence through spacetime. Nothing with mass can be accelerated to that speed, let alone beyond it. As an object with mass moves faster and faster, the energy required rises more and more dramatically. The closer you get to light speed, the more impossible it becomes to go further. This is not a failure of engineering. It is not a problem waiting for a better engine. It is part of how the universe appears to be built. So now we can begin to see the contour of the trap. If you imagine an object whose gravity is so strong, and whose mass is packed so tightly, that the escape velocity at a certain distance becomes equal to the speed of light, then something profound happens. At that distance, even light emitted outward would barely fail to get away. If you go any closer, then the escape velocity becomes greater than light speed. And since nothing can move faster than light, nothing can escape from within that boundary. Not a spaceship, not a signal, not a particle arranged into a human body with every resource in the universe behind it. Nothing. That boundary is what we call the event horizon. But even before naming it again, you can already feel its logic. The event horizon is not magical. It is not a cosmic wall. It is the place where the speed required to escape becomes greater than the highest speed reality allows. That is why black holes are not just strong versions of ordinary objects. They are a different category of consequence. Let us make it gentler again. Picture a child tossing a paper airplane indoors. It flies across the room and lands softly on the floor. Now picture trying the same thing outside in a strong wind. Suddenly the same throw behaves differently. The airplane struggles, turns, drops, or is pushed back. Now imagine the wind growing so fierce that no matter how skillfully you throw, no paper airplane can make headway against it. At first, that is only difficult. Then it becomes hopeless. Near a black hole, gravity is not exactly wind, of course. But the feeling of a threshold turning into impossibility is similar. Below a certain severity, escape is hard. Beyond a certain severity, escape is no longer a matter of courage, effort, or design. It simply does not exist as an option. And the deeper truth is even stranger than that. Because in the most modern picture, especially through Einstein's relativity, gravity is not merely a force pulling on objects. It is the curvature of spacetime itself. Objects follow the shape of that curvature. So when escape becomes impossible, it is not just because something is pulling too hard. It is because the geometry of reality has bent so deeply inward that all allowed paths lead the wrong way. That is what makes black holes so unsettling. They do not just overpower motion. They redefine what motion can mean. Still, one of the loveliest things about science is that even the strangest ideas can often be reached from ordinary experiences. Throwing a stone, jumping into the air, watching a rocket rise, looking at the moon and realizing it can be left more easily than Earth. Understanding that stars, too, have escape velocities. Understanding that more mass and less size deepen the well. Little by little, the mind gets ready. And perhaps that is why black holes are so compelling for beginners as well as experts. They feel impossible at first, like something too far from everyday life to grasp. But if you begin with a stone and the earth and a hill and a rocket, the road to the abyss becomes surprisingly continuous. The laws do not suddenly change when you get to black holes. They simply keep going. And that may be the most haunting part of all. The universe does not need to invent new rules to create something inescapable. The old rules are enough. A star collapses. Mass compresses. Gravity intensifies. Escape velocity rises. And then, at last, a threshold is crossed. You could almost say that a black hole is born when nature takes the idea of escape velocity to its logical conclusion. There is something elegant in that. Terrifying, perhaps, but elegant. A black hole is not chaos. It is precision taken to an extreme. It is what happens when gravity and compactness combine so completely that even light can no longer win the race outward. That phrase, even light, matters because light is usually the messenger that makes the universe visible to us. We know stars exist because their light reaches us. We know galaxies exist because their light travels across millions or billions of years and arrives at our telescopes. We know much of reality by what escapes from it and reaches our eyes, our detectors, our instruments. So when a place is born from which light cannot escape, it becomes not just dangerous, but hidden. It withdraws from direct view. It becomes a presence known mostly through effects, shadows, or what happens around it. That is why the phrase black hole is so fitting. Not because there is a literal hole in space, but because it is a region that withholds light itself. And the reason it withholds light leads straight back to the simple question we began with. What does it take to get away from gravity? For Earth, the answer is already enormous. For the Sun, larger. For a neutron star, astonishing. For a black hole, beyond the limit. And once you begin to feel that progression, the title of our journey starts to settle in with a different weight. Why escaping a black hole is truly impossible is not dramatic because it sounds frightening. It is dramatic because it is precise. The impossibility is not poetic exaggeration. It is a direct consequence of escape velocity colliding with the universal speed limit. There is no hidden tunnel out. No last-second burst of engine power. No clever route that physics forgot to close. Because the problem is not that escaping is too hard. The problem is that it would require something reality does not permit. And maybe there is something almost calming in that clarity. Severe, yes, but clear. The black hole is not malicious. It does not choose to trap. It simply exists in a state where the path outward has been removed from the list of possible futures. If these quiet journeys through space help ease you towards sleep, you can leave a like, subscribe, or share a thought in the comments about which idea feels stranger to you. That stars can collapse into black holes, or that the key to understanding them begins with something as simple as throwing a stone into the sky. For now, though, hold on to this one idea. Escape velocity is the speed needed to leave gravity behind. Every world has one. Every star has one. And when that required speed rises beyond the speed of light, a black hole has drawn its invisible boundary. In the next part, we move closer to that boundary itself. Because once you understand what it means to escape gravity, the next question arrives naturally, and with it, one of the most unsettling facts in all of physics. If not even light can get out, then what does that really mean for anything that falls in? Part 4. Why light cannot get out. By now, the idea is beginning to settle into place. A black hole is not simply an object with strong gravity. Plenty of things in the universe have strong gravity. Massive stars do. Neutron stars do. Even our own Earth, gentle as it feels compared with those extremes, still holds us tightly enough that leaving it requires enormous speed. What makes a black hole different is not just strength. It is finality. There comes a point near a black hole where the question is no longer whether escape would be difficult, expensive, dangerous, or unlikely. The question becomes much simpler than that. Can anything get out at all? And the strange, quiet answer is no. Not even light. That phrase has become famous over the years. It appears in documentaries, science books, articles, classroom explanations, and late-night conversations about the universe. But because it is repeated so often, it can start to lose some of its meaning. It becomes a slogan before it remains an idea. So let's slow it down. Let's sit with it carefully. Because when physicists say that not even light can escape a black hole, they do not mean light is weak. They do not mean light gave up. They do not mean the black hole somehow reaches out and grabs light like a hand closing around an object. They mean something deeper. They mean the very structure of spacetime around the black hole has become so severely curved that all possible outward paths have been closed. And that is one of the reasons black holes feel so unsettling. They do not defeat motion by brute force alone. They defeat it by changing the landscape on which motion happens. But perhaps the best place to begin is with light itself. Light is, in many ways, the great messenger of the universe. Almost everything we know about the cosmos has come to us because light carried that knowledge across space. We know the sun is there because its light reaches Earth every morning. We know distant stars exist because their light crosses light years of darkness to arrive at our eyes and telescopes. We know what galaxies look like, what nebulae are made of, how planets move, how the universe expands, because light keeps bringing us news from places we can never touch. Light tells us where things are. It tells us what they are made of. It tells us how hot they are, how fast they are moving, whether they are approaching or receding, whether they are young or ancient, calm or violent. Light is how the universe introduces itself. And light, by all appearances, moves as fast as anything can. That matters. Because if even light cannot get away from a certain place, then that place is not merely hard to leave. It has crossed into another category entirely. It has become hidden in principle, not just in practice. Imagine you are in a valley at night with a lantern in your hand. If the valley is shallow, the lantern light spreads outward in every direction. It climbs the slopes, reaches the trees, spills over the edges, and can be seen from far away. If the valley is deeper, more of the surrounding land blocks and contains the glow. But still, light escapes. It rises. It spreads. It finds its way out. Now imagine a valley so deep, so severe, and so strangely shaped that every direction the light tries to move is bent back inward. The lantern still shines. Light still leaves the flame, but it cannot make its way to the wider world. Every path curls back into the depths. That is closer to what a black hole does. Not because light suddenly forgets how to travel, but because the geometry around it has become inescapable. Outside a black hole, light behaves in ways we already know, at least in broad outline. It moves through the cosmos, bending slightly when gravity is present. If it passes near a star or galaxy, its path curves. This effect, called gravitational lensing, has become one of the most beautiful confirmations of Einstein's picture of gravity. Massive things bend space-time, and light follows the bend. That last part is important. Light follows the shape of space-time. So if space-time near a black hole is curved gently, light bends gently. If space-time is curved more strongly, light bends more strongly. And if space-time is curved so extremely that every future directed path points inward, then light goes inward too. That is the real secret. A black hole does not need to overpower light in the ordinary sense. It does not need to chase it down or cancel its speed. Light is still doing what light always does. It is moving along the available paths of spacetime. The problem is that inside a certain boundary, there are no outward paths left for it to follow. This is why the event horizon matters so much. At the event horizon, the situation becomes exact. It marks the boundary where the escape route closes. Far away from the black hole, a beam of light pointed outward can move outward just fine. Closer in, it still can, though gravity bends its route and affects its energy. But at the horizon, something profound changes. The outward direction becomes more like a pause at the edge of failure. And once the light is emitted from inside that boundary, even if it is aimed outward, it still ends up moving toward the center. That may be one of the most difficult things for the imagination to accept. We are used to thinking that outward is a direction you can always choose. If you are in a room, outward is toward the door. If you are underwater, upward leads toward air. If you are in a valley, uphill leads toward escape. But inside a black hole, those ordinary intuitions begin to fail. Inside that region, pointing outward is no longer enough, because the future itself leans inward. And perhaps that phrase is the gentlest way to say it. The future leans inward. Light is not escaping because there is no future available to it that leads out. That is a more subtle idea than gravity pulls too hard, though the two are related. The phrase about gravity pulling too hard is a useful shortcut. It helps us get started. But Einstein's universe goes further than that. Gravity is not just a pull. It is the shape of space-time. And once that shape becomes extreme enough, leaving is not difficult in the way climbing a steep hill is difficult. It is impossible in the way tomorrow cannot lead backward into yesterday. And that is why black holes are so much stranger than deep pits or strong magnets or powerful engines. They change the map. It may help to think about a river again. Imagine you are floating in a small boat. Far upstream, the river is gentle. You can paddle in any direction. You can move toward one bank, the other bank, or back upstream if you have the strength. As the current grows stronger, paddling against it becomes harder, but still possible. Then you reach a point where the current matches your best effort. You can no longer gain ground upstream, though you can hold position for a while. Drift just a little farther, and now even your strongest paddling fails. Every choice you make still ends with the river carrying you down. Now imagine replacing yourself with a beam of light, and replacing the river with the inward flow of space-time near a black hole. That is not a perfect analogy, of course, but it captures something essential. Light is not becoming slower in its own local experience. It is still the fastest thing there is. But the stage on which it moves has tilted so completely inward that even its speed cannot take it back out. This is one reason black holes feel almost philosophical. They take an ordinary human instinct, the instinct to think that enough effort can solve a problem, and they place a hard limit in front of it. Usually, if something cannot get out, we imagine adding more power, a stronger engine, a larger explosion, a better design, a more advanced civilization. But black holes are not impressed by that logic, because the barrier is not technological. It is geometrical. Once you are too far in, no engine helps, because no engine can create a path where space-time no longer provides one. And since light already travels at the maximum speed available to causation in the universe, even it cannot do better. That is why physicists often treat light as the perfect test case. If light fails to escape, everything else must fail too. Not because light is special in a mystical way, but because it already lives at the upper limit. If the fastest messenger cannot carry news out, then no slower traveler ever will. This also explains why black holes appear black. That darkness is not cosmetic. It is not because the surface is painted dark or because the environment lacks illumination. A black hole appears black because light from within the event horizon does not reach us. No image can come directly from inside. No direct glow carries information from beyond that boundary to the outside universe. It is silence in visual form. Of course, the area around a black hole can be astonishingly bright. Gas falling inward can heat up and shine. Matter in an accretion disk can blaze with X-rays. Some supermassive black holes launch enormous jets that light up space across incredible distances. In those cases, the black hole's surroundings can become some of the brightest regions in the universe. But the black hole itself remains dark. That dark center in those famous black hole images is not an artistic choice. It is the visible consequence of missing light. We are seeing the outline of where escape has failed. And there is something haunting in that. We do not see the black hole the way we see a star. We see the absence it creates. We see the brightness around it. We see the distortion of the background light. We see stars orbiting something invisible. We see matter heating, accelerating, disappearing. We see the shadow. A black hole is, in a sense, revealed by what it prevents. That alone makes it different from almost every ordinary object we know. If you think about it long enough, it begins to feel almost poetic that the universe's most famous invisible object is understood through the fade of light. Light is our main way of knowing, and black holes are where knowing runs into a wall. Or rather, not a wall, a horizon. That word matters. Horizon is softer than wall, and more accurate too. A wall suggests impact, resistance, a solid thing you crash into. A horizon is more subtle. It is a boundary of visibility. It is the line beyond which something no longer sends news back. Here on Earth, the horizon hides ships when they move far enough away. The ship is still there, but beyond the line of sight. A black hole's event horizon hides in a more severe way. It is not just beyond a line of sight. It is beyond a line of return. That is why light becomes such a central character in the story of black holes. Not because it suffers in some dramatic sense, but because it defines what the rest of the universe can know. If light cannot escape, then information about what happens inside becomes sealed away from outside observers. And once information is trapped, the black hole becomes not just a physical place, but a limit on observation. That has consequences far beyond appearances. For example, imagine someone falling toward a black hole while carrying a flashlight. As long as they remain outside the event horizon, at least in principle, some of the light from that flashlight can still reach the outside universe. It becomes redder and weaker as the gravity deepens, but it can still escape for a while. To a distant observer, the person seems to slow down and dim, their light stretched toward longer wavelengths by gravitational redshift. That redshift is one of the quiet but important effects here. When light climbs out of a gravitational field, it loses energy. Since the energy of light is related to its frequency, losing energy means its frequency drops and its wavelength stretches. Blue light shifts toward red. Red light shifts toward infrared. Infrared shifts farther still, into wavelengths the human eye can no longer detect. So even before the event horizon is crossed, the escaping light grows weaker in a very real sense. It becomes more tired, if you want a gentle metaphor. It spends energy climbing out of gravity's well. The deeper it starts from, the more drained it becomes. At the horizon, the struggle becomes total. Beyond it, no light from the traveler's flashlight can ever make the journey outward. The outside universe no longer receives updates. It loses contact not because the flashlight turned off, but because the pathway back has vanished. And that leads to one of the strangest emotional aspects of black holes. From the outside, it can look as though a falling object never quite disappears in the simple way we might expect. Instead, it seems to slow, fade, redden, and asymptotically approach the horizon. The final signals become weaker and weaker. The image lingers as a dimming ghost. But for the person falling, nothing special has to happen at the horizon itself, especially if the black hole is large enough. Their flashlight still works. Their heartbeat continues. Their thoughts continue. Locally, they are not aware of some flashing sign that says you have now passed the point of no return. This difference between what the outside sees and what the falling observer experiences is part of what makes black hole physics so psychologically strange. It is not merely one weird fact. It is a web of weird facts, all woven together by relativity. Still, beneath all that strangeness, the core logic remains wonderfully clean. Light cannot get out because within the event horizon there is no route outward that the universe allows. Not because light slows below its own limit. Not because gravity acts like a hand around a throat. Not because the black hole is hungry. But because spacetime has become shaped in such a way that all future directed motion leads inward. And once you understand that, a lot of other mysteries begin to quiet down. You no longer need to imagine some mysterious sucking force pulling everything in from absurd distances. Black holes do not behave that way. From far away, they can be orbited like other massive objects. If our sun were magically replaced by a black hole of the same mass, Earth's orbit would remain almost exactly the same. The life would clearly become impossible for more obvious reasons. Gravity at a given distance depends on mass, and a black hole does not gain magical extra pull just by being a black hole. The difference emerges when you get close. Very close. That is where the geometry becomes severe enough to matter in the black hole sense. That is where light paths curve dramatically. That is where escape velocity climbs beyond the possible. That is where the event horizon becomes real. And once there, the old human language of effort begins to lose its usefulness. Try harder no longer means anything. Aim better no longer means anything. Move faster no longer means anything. Because the problem is not a challenge in the ordinary sense. The problem is that out has stopped existing as a reachable future. Perhaps that is the most unsettling sentence in this entire journey. Out has stopped existing. For creatures like us, whose lives are built around choices and directions and alternate paths, that idea feels almost unbearable. We are used to exits. We are used to turning around. We are used to last chances. Even in danger, some part of the mind imagines one more option, one more move, one more escape route hidden somewhere in the dark. A black hole takes that instinct and calmly removes it, not with violence, but with awe, not with anger, but with geometry. And that is why the impossibility of escape feels so profound. It is not just another example of the universe being powerful. It is the universe drawing a line and saying that beyond this point, the story only goes one way. If these slow explorations help you rest, you can leave a like, subscribe, or mention in the comments which black hole idea feels most surreal to you so far. That light cannot escape, that time looks different near the horizon, or that the darkness of a black hole is really a silence of information. For now, though, keep hold of this one truth. Light is the fastest messenger in the universe, and even light cannot escape once it begins from inside the event horizon. That means the black hole is not just dark. It is sealed. And in the next part, we move even closer to the edge itself, to the invisible boundary where all of this becomes final, and where a very strange phrase begins to make perfect sense. The point of no return. Part 5, the event horizon, the point of no return. There is something especially unsettling about an invisible boundary. A cliff can be seen. A storm can be heard. Fire announces itself with light and heat. Even deep water often gives some warning, a change in color, a drop in the ground, the hush that comes just before your foot loses contact with what felt solid a moment ago. But an event horizon offers none of that. No sign. No surface. No glowing line drawn neatly across space to say, beyond this point, the universe changes its mind about what escape means. If you were drifting toward a black hole, there would be no cosmic fence ahead of you. No last marker suspended in the dark. No physical barrier for your hand to touch. And yet, there it is. A boundary more absolute than stone, more final than steel, and more unforgiving than anything built by human hands. The event horizon. This is the place where the story of a black hole becomes more than just a story about strong gravity. It becomes a story about direction itself, about what futures remain possible, and which ones have quietly disappeared. Up to this point, we have moved gently toward the idea. We have watched massive stars exhaust their fuel and collapse under their own weight. We have followed the rise of escape velocity, from the Earth to stars to the unimaginable severity of a black hole. We have seen why even light cannot get out, not because it becomes weak, but because the outward path is no longer available to it. Now we arrive at the line where all of those ideas meet. The event horizon is not just the edge of a black hole in the visual sense. It is the edge in the physical sense, the mathematical sense, and almost the philosophical sense too. Outside it, return is still possible, at least in principle. Inside it, the idea of return is gone. That is why people call it the point of no return. And unlike so many dramatic phrases in popular science, this one is not exaggeration. It is almost too gentle. If anything, it understates the situation. Because when you cross the event horizon, you do not merely lose the ability to climb back out the way a hiker might lose the ability to climb back up a steep hill. You lose access to any future in which out remains part of the story. That is what makes it so strange. To begin to feel it properly, it helps to let go of one of the most natural assumptions the human mind carries around. We assume space is basically neutral. We assume that if we are somewhere, directions remain available. Forward, backward, left, right, up, down. Some choices may be harder than others, some may be dangerous, some may require more energy, but the directions themselves still exist. Near a black hole, and especially at the event horizon, that ordinary trust begins to fail. Imagine walking through a thick fog in a wide open field. You cannot see very far, but you know the field continues around you. Even if you are disoriented, you still believe that one direction leads back to the road, another toward the trees, another toward the house you came from. The world remains open. Your confusion is temporary. Now imagine a much stranger kind of world. One in which, as you move deeper into the fog, the landscape itself changes so completely that every path available to you, no matter which way you turn, slopes toward the same destination. Not because you are choosing badly, not because you are tired, but because the terrain has been shaped so thoroughly that all roads now descend together. That is closer to the truth of the event horizon. The event horizon is where the geometry of spacetime becomes committed. Beyond that boundary, every future directed path leads inward. You may still feel as if you are moving normally. You may still think of yourself as choosing. You may even point your ship outward and fire the engines with perfect discipline. But none of that can restore the path that no longer exists. And perhaps that is what makes the event horizon so much colder than a wall. A wall resists you. A horizon simply reveals that the world ahead has changed. If you were to fall toward a black hole, especially a very large one, nothing dramatic would necessarily happen at the precise moment you crossed the event horizon. That detail surprises many people the first time they hear it. There is a natural instinct to imagine some kind of cosmic impact, a shock, a tearing sensation, a flash of impossible light, some obvious signal that you have crossed from one regime into another. But the universe is often quieter than that. If the black hole is massive enough, the local conditions at the event horizon can actually be quite gentle. You might cross it without feeling a thing. Your body would not strike a surface because there is no surface there. Your clock would continue ticking. Your heartbeat would continue. If you were looking out the window of a ship, the stars might still be visible, though distorted in increasingly strange ways. And that is part of the horror, if we are honest. Not that the boundary is violent, but that it can be ordinary. The most final crossing in the universe may happen in silence. This is one reason black holes continue to fascinate people who are not physicists. They are not just powerful objects. They produce situations that seem to reach directly into the human imagination. The event horizon is one of those situations. It is a place where common sense does not break all at once, but slowly enough that you can still recognize yourself inside the confusion. You cross, and the ordinary rhythm of your own experience may barely change, but the meaning of your future has changed completely. It helps, again, to return to the river. Imagine a river flowing toward a waterfall. Far upstream, the water is calm. You can swim wherever you like. You can angle toward the banks, float downstream, or strike hard against the current and make your way back. As you move closer to the falls, the current strengthens. Swimming upstream becomes more difficult. Closer still, you reach a line where the current matches your best possible speed. You can hold position, perhaps for a moment, but no more. That line, in the analogy, is the event horizon. If you drift just beyond it, the current is now stronger than anything you can do. Even if you swim with perfect technique, even if you are stronger than any swimmer who has ever lived, the river has stopped offering an upstream future. You can still move your arms. You can still turn your body. You can still make local choices. But all of those choices now happen inside a larger flow that only goes one way. The event horizon is like that, except deeper and stranger. Because what is flowing inward is not water. It is spacetime itself. That phrase can feel abstract, but it matters. The reason the event horizon is not just an ordinary boundary of speed is that it emerges from the shape of the universe around the black hole. Space and time, which already behave differently from what intuition suggests, become increasingly distorted near the horizon. Outside it, there are still future paths that lead away. Inside it, all future paths point toward the center. This is why physicists sometimes say that inside the event horizon, moving toward the singularity is as unavoidable as moving toward tomorrow. That is an astonishing sentence when you really pause with it. You do not choose to move into the future. You simply do. You can delay tasks. You can pause your speech. You can rest in bed and do nothing at all. But you cannot refuse tomorrow. Time carries you whether you cooperate or not. Inside a black hole, the journey inward takes on something like that inevitability. The singularity is no longer merely ahead of you in space. In an important sense, it lies ahead of you the way the next moment of time lies ahead of you. It is not just somewhere you could go. It is somewhere your future leads. That is why escape becomes impossible in such a deep way. It is not just hard to reverse course. Reversing course would require stepping outside the structure of possible futures that spacetime now permits. And this is also why the event horizon is such a decisive concept in physics. It separates what can still communicate with the outside universe from what cannot. Once something crosses that horizon, it may continue to exist for some time from its own perspective. It may continue falling. It may continue sending out light locally. But none of that information can ever return to the wider cosmos. The outside universe loses access. The story becomes one-sided. This has a subtle emotional consequence too. A black hole is not only a trap for matter. It is a trap for narratives. Once something passes the event horizon, there is no more reporting back. No more updates. No final message delivered across the dark. The outside can only infer, never witness directly. And the last image it receives becomes stranger the closer you get to the horizon. To a distant observer, your approach would appear to slow. This is one of the great weirdnesses of relativity. As you move deeper into the black hole's gravitational field, the time measured by your clock and the time measured by someone far away no longer match in the intuitive way we expect. To the distant observer, your clock appears to tick more and more slowly. The light coming from you is redshifted, stretched to longer wavelengths, losing energy as it climbs out of the gravitational well. So what does that mean visually? It means you would seem to fade. First, perhaps, everything looks almost normal. Then the signals from you begin to redden. Your movements appear slower. The glow from your ship weakens. The image becomes dimmer and dimmer, more drawn out, more ghost-like. To the person watching from far away, it may seem as though you never quite crossed the horizon at all. Instead, you appear to freeze near it, fading into darkness with agonizing slowness. That does not mean you really stop there in your own experience. For you, time continues. You cross the horizon after a finite amount of your own proper time. You do not feel yourself freezing in place. You do not hover forever on the edge. You continue inward. And this difference, between the outside view and the falling view, is one of the reasons the event horizon has such a mysterious reputation. It sits at the meeting point of two truths that seem impossible to reconcile at first glance, yet both belong to the fabric of relativity. From far away, the horizon is approached but never visibly crossed. From the falling traveler's own perspective, it is crossed quite normally. Both descriptions arise from the same universe. That may be one of the most beautiful and unnerving things Einstein gave us. Reality does not always come with one single viewpoint that feels comfortably complete. Different observers can tell the story differently, and both can still be right within their own frame of reference. The event horizon lives inside that strangeness. But perhaps we should slow down again, because there is a temptation here to let the mathematics feel more complicated than the emotional truth really is. The emotional truth is simple. Outside the horizon, there is still hope in principle. Inside it, there is not. That is why the horizon matters so much. It is the last line separating a region where the universe still allows return from a region where it does not. And because the boundary is invisible, it forces us to confront something deeper than fear of impact or collision. It asks us to imagine irreversible change without visible drama. Human beings are not especially comfortable with that. We like warnings. We like obvious thresholds. We like pain before injury, smoke before fire, cracks before collapse. But the event horizon is more like a sentence whose meaning changes halfway through even though the words stay calm. You read forward, still thinking you understand where things are going, and only later realize you passed the point after which the ending had already been decided. That is the horizon. One quiet crossing. One invisible decision made by the geometry of spacetime. And after that, even though your personal experience continues, the universe beyond can no longer be reached by anything you do. If you imagine a beam of light being emitted outward just before the event horizon, it can still escape, though perhaps weakened and redshifted. At the horizon itself, the situation becomes more delicate. And from just inside it, even a light beam pointed outward cannot make its way to infinity. That is how exact the boundary is. It is not a vague region of maybe. It is a clean divide in the logic of escape. That precision is one reason scientists care so deeply about event horizons. They are not just poetic notions. They are exact features of spacetime predicted by general relativity and tied to the causal structure of the universe. They tell us which events can influence which other events. They mark the edge of causal disconnection from the outside world. But even that technical phrase, causal disconnection, becomes gentler when translated back into ordinary language. It means after a certain point, nothing you do can matter to the outside anymore. No signal, no light, no warning, no goodbye. That quiet severity is what gives the event horizon its power over the imagination. It is not only a scientific idea, it is a symbol of irreversibility in its purest form. And yet, like so many things in the universe, it is not cruel in any personal sense. The event horizon does not choose. It does not punish. It does not trap out of intention. It simply follows from the existence of a black hole. Once enough mass is compressed into a small enough region, once the escape velocity exceeds the speed of light, the horizon appears as naturally as a shadow appears when something blocks the sun. Nature does not need emotion to be absolute. It only needs law. There is another subtle beauty here too. The event horizon teaches us that a boundary does not have to be made of matter to be real. We often think a real thing must be tangible, solid, or at least visible. But the event horizon is none of those, and still it may be one of the most consequential boundaries in the universe. It is made, in a sense, of possibility. Or rather, of the loss of possibility. That is enough to make it real. This is why the phrase point of no return lands with such force. It does not mean danger is now nearby. It means danger has become woven into the structure of what comes next. And as we continue inward, another question begins to rise, almost against our will. If the event horizon is the place where return ends, what would crossing it actually feel like? Would you know? Would your body notice? Would your thoughts change? Would the stars outside seem the same, or would the universe begin to distort in ways too strange to bear? Those questions matter because the event horizon is not the end of the journey. It is only the end of escape. The fall itself continues. And what comes after depends very much on the size of the black hole, the path you take, and the tidal forces waiting deeper in. But for now, it is enough to stay with the boundary itself. An invisible line. A silent crossing. A place where the universe stops offering exits. If these slow explorations are helping you rest, you can gently leave a like, subscribe, or tell me in the comments which part of black hole physics feels strangest to you so far. Not the most frightening, necessarily, but the strangest. The invisible horizon, the fading of time from the outside view, or the idea that out can simply stop being part of the future. For now, though, let the image settle. You are drifting through darkness toward a region that does not announce itself. There is no wall ahead, no surface, no alarm. Only space, quiet and black, and a boundary you cannot see. A moment comes. It feels ordinary. Your breath is steady. Your ship is intact. Your hands still move. Your mind still thinks in the same calm rhythm. And then, without sensation, without sound, and without any visible sign at all, you have crossed the last line from which the universe still allowed you to return. In the next part, we move beyond the horizon's definition and into something even stranger. Because once you understand the event horizon as the point of no return, a new question becomes unavoidable. What if you had the best ship ever built, the most powerful engines imaginable, or a civilization far more advanced than our own? Would trying harder make any difference at all? Or has the horizon already made effort itself irrelevant? Part 6. Why trying harder changes nothing. There is a very human instinct that stays with us almost all our lives. If something is difficult, we try harder. If a door is heavy, we push with more force. If a hill is steep, we lean forward and keep climbing. If a machine begins to fail, we improve the design, upgrade the motor, strengthen the frame, and search for a smarter solution. Much of human progress has come from that stubborn and beautiful refusal to stop at the first obstacle. When nature presents a challenge, we answer with effort. When effort is not enough, we answer with invention. That instinct has taken us across oceans, into the sky, onto the moon, and deep into the hidden structure of matter itself. It has taught us to trust that somewhere, beneath the surface of a problem, there is usually a way through. So when people first hear about black holes, especially the event horizon, they often ask a very natural question. What if you had a better ship? What if your engines were unimaginably powerful? What if your civilization were millions of years more advanced than ours? What if you had limitless fuel, perfect navigation, materials stronger than anything we can currently imagine, and a pilot calm enough to make every decision exactly right? Would that change anything? Could you escape then? It is such a reasonable question that it almost feels rude for physics to answer the way it does. No. And the reason for that no is one of the most important things to understand about black holes. Because if escaping a black hole were only a matter of insufficient power, then the situation would still belong to the ordinary world. It would be like launching from Earth, except much harder. It would be like climbing out of a deeper canyon, except more dangerous. It would still be a contest between your technology and gravity. But once you cross the event horizon, that is no longer the kind of problem you are facing. You are no longer asking whether your engine can overcome the pull. You are asking whether it is possible to travel toward a future that spacetime no longer allows. And those are very different questions. To feel that difference properly, it helps to begin with something more familiar. Imagine you are walking through a city with streets laid out in a perfect grid. You can go north, south, east, or west. Some routes are longer, some are crowded, some are blocked by traffic, but the city is open in principle. If you want to reach a certain place, you can try faster transport, better planning, or more stamina. The problem is difficult only in the practical sense. Now imagine something much stranger. Imagine a city where, beyond a certain district, every road begins curving toward a single center. At first the bends are slight. You can still navigate. But deeper in, every street, every tunnel, every bridge, every available route, no matter where it begins, now leads toward the same place. You can still move. You can still choose between roads. But all the roads eventually agree. At that point, a faster car does not solve the problem. A larger engine does not solve the problem. Even a flying machine would not solve the problem if the air corridors themselves had been bent the same way. Because the issue is no longer weakness. The issue is that the map has changed. That is what the event horizon does. It does not merely make escape harder than we can currently manage. It changes the causal map of reality so thoroughly that every future directed path leads inward. And that is why, trying harder, changes nothing. Human beings are very good at solving force problems. We are less comfortable with geometry problems, especially when the geometry is not the shape of an object, but the shape of possibility itself. Outside the event horizon, greater power can still matter. If you are orbiting a black hole from a safe distance, and you fire your engines at the right moment, you can leave. If you are falling toward it but have not yet crossed the horizon, a sufficiently strong burn might still save you. The closer you are, the more extreme the demand becomes. But the logic remains familiar. There is still an outside. There is still a route back. There is still a future that includes escape. That is why the event horizon matters so much. It is not just another point along a gradient of danger. It is the dividing line between a hard problem and an impossible one. Before the horizon, the universe still contains a version of your future in which you get away. After the horizon, it does not. This can be surprisingly hard to accept, because so much of ordinary life is built around the belief that effort scales. We assume that if a problem defeats us, it might still be defeated by something stronger. If we cannot lift a boulder, perhaps a crane can. If a car cannot climb a mountain road, perhaps a truck can. If chemical fuel is not enough, perhaps nuclear power is. If one species cannot survive a climate, perhaps another can. We are used to the idea that limits are often local. But the event horizon is not a local engineering limit. It is not like saying, our rockets are not good enough yet. It is more like saying, the direction you want no longer exists within the future light cone of your position. That phrase, future light cone, belongs to relativity, but its meaning can be held gently. At every moment, the universe offers a set of possible futures. You can move slowly, quickly, left, right, sit still, walk, accelerate, change course. Light also has its set of allowed trajectories, and because it travels at the universal speed limit, those trajectories define the outermost edge of what can be influenced from a given event. Outside a black hole, some of those future possibilities point outward. Inside the event horizon, they do not. So when someone asks, what if I had the best engine in the universe? The answer is still no, because the engine would be trying to do something deeper than produce force. It would be trying to create an outward future where none exists. And physics, calm as ever, simply refuses. Imagine trying to drive south on a road that has become time itself. You cannot choose north instead, because north is no longer a road available to you. Or imagine trying to arrive at yesterday by building a faster train. No matter how excellent the train is, yesterday is not a destination hidden behind poor performance. It is outside the structure of what motion can do. That is closer to what escape looks like from inside a black hole. Not a route that is very hard. A route that is not there. This is why black holes produce such a different kind of helplessness from the ordinary dangers we know. Most dangers still leave room for heroism in the familiar sense. A storm can be survived. A mountain can be descended. A fire can be outrun. A failing spacecraft can sometimes be repaired or redirected. We admire courage partly because the world usually leaves some space for it to matter physically. The event horizon is different. Courage may remain meaningful emotionally, even spiritually, if we want to use a human word like that. Calmness may still matter. Grace may still matter. But force no longer matters. Technique no longer matters. Better engines no longer matter. It is not a contest anymore. And perhaps that is why black holes feel so absolute. They strip away the hopeful exaggeration that effort can always buy another chance. There is a classic thought experiment people often stumble into at this point. They say, all right, perhaps ordinary engines are not enough. But what if I had infinite power? It sounds like a cheat code, and in ordinary conversation it often is. Infinite power is the kind of phrase people reach for when they want to escape the burden of constraints altogether. If the problem is speed, then infinite power gives infinite speed. If the problem is force, then infinite power gives infinite thrust. But physics is not impressed by that phrase. Even before we talk about black holes, infinite power begins to run into trouble. Real theories do not welcome infinities easily. They are usually signs that language has outrun physical meaning. But even if we grant the fantasy for a moment, the event horizon still resists it. Why? Because the problem is not energy in the ordinary sense. The problem is causal structure. Suppose you are inside the event horizon and somehow possess an engine of absurd strength. You fire it outward. What does that mean? In ordinary space, it would mean you accelerate in the outward direction and perhaps climb free. But inside the horizon, outward is no longer a future direction you can access. Your engine can alter your path within the set of allowed inward futures, but it cannot reopen a path that leads outside the horizon any more than raw strength can turn east into tomorrow. That sounds strange because our minds always want to put engines ahead of geometry. We think power creates options. In daily life, it often does. But black holes remind us that options are only meaningful within the structure of the world. A fish can swim beautifully, but if it is caught in a waterfall where the water itself is falling faster than any fish can swim upward, skill no longer changes the basic outcome. The fish still moves. It still makes local adjustments. It still experiences the water and responds to it. But the larger flow has already decided the overall direction. And even that analogy is softer than the truth. Because in the waterfall case, we can still imagine a helicopter lowering a net, or a side current, or a lucky rock. There are still external possibilities. Inside the event horizon, there are not. Nothing from outside can reach in and pull you back out in a way that restores escape as a future. Once you are across, the condition is not like being trapped in a dangerous place. It is like inhabiting a region of spacetime whose every tomorrow points deeper inward. Another instinct people have is to imagine some incredibly advanced civilization bending the rules. Perhaps, they say, a civilization billions of years older than us could manipulate gravity itself, open wormholes, punch holes through space-time, or step into higher dimensions. Science fiction lives there, and beautifully so. There is nothing wrong with imagination going that far. In fact, imagination is often what keeps science emotionally alive. But when we ask the narrower question, according to the laws of physics as we understand them, can trying harder help once you are inside the event horizon? The answer remains no. Could unknown physics one day revise our picture of the deepest interior of black holes? Possibly. Science is always open to deeper truth. We do not yet possess a complete theory of quantum gravity. We do not know every detail of what happens near the singularity. We do not know whether some of our current pictures will eventually be replaced by more complete ones. But that uncertainty does not really rescue the event horizon in the way people often hope. The reason is simple. The horizon is not a vague speculation. It emerges quite robustly from general relativity, from the geometry of collapse, and from the observed behavior of black hole-like objects. The details of the center may remain mysterious, but the point of no return structure is not just a casual guess. So even if the final theory turns out stranger than we currently imagine, the basic lesson is likely to remain severe. The inescapability is not just a failure of our present rockets. It is built into the logic of the horizon itself. Perhaps there is another way to feel this. Imagine reading a novel where, halfway through, you discover that every chapter after a certain page leads toward the same ending. The characters can still speak, move, and make choices. The story continues. But some deeper freedom has already been lost. There is no chapter hidden later in the book where the plot suddenly escapes into an entirely different genre. The structure has committed itself. The event horizon is like that for spacetime. You keep existing. Things keep happening. But the narrative possibilities have narrowed to one direction only. And yet, even within that narrowing, there can still be local differences. This is worth noticing, because otherwise the interior of a black hole can start to feel too empty as an idea. Once inside the event horizon, not everything becomes instantly identical. You can still accelerate. You can still rotate. You can still emit light locally. You can still change how quickly you reach the deeper regions. Different trajectories may matter. For example, you might fall straight in, or orbit inward for a while if such motion is still available in that region, depending on the black hole and the exact path. Your choices can affect your experience, but they cannot affect the final fact that you do not get back out. That distinction is important because it makes the black hole even stranger. It is not a place where all motion stops. It is a place where motion continues under a new law of fate. Freedom becomes local, not global. You can still choose how you fall. You cannot choose not to fall. That is an almost tragic sentence, though it is also physically precise. And perhaps it touches something human in us because life itself sometimes feels that way. There are situations where the broad outcome cannot be reversed, and all that remains is the shape of one's conduct within it. The event horizon turns that emotional truth into a piece of geometry. There is another reason trying harder fails, and it has to do with the speed of light itself. If you are outside the horizon, escaping requires speed, yes, but still within the structure of possible motion. If you are exactly at the threshold, the required outward motion asymptotically reaches the speed of light. Beyond the threshold, escape would require faster than light travel relative to the relevant geometry. And here again, physics closes the door. Nothing carrying information or matter is known to move through spacetime faster than light. That is not simply a technological embarrassment. It is woven into relativity at the deepest level. To demand escape from inside the horizon is, in effect, to demand access to a kind of motion the universe does not seem to permit. So a stronger engine is like a louder voice in a vacuum. It may feel powerful, but it is aimed at the wrong layer of the problem. This is one reason black holes have such enormous philosophical weight. They remind us that not every can't in the universe is temporary. Some can'ts are local failures of technology. Others are expressions of how reality is shaped. And black holes belong to the second category. That does not make them magical. Quite the opposite. It makes them more profound, because they emerge from ordinary laws followed all the way to an extraordinary conclusion. A star collapses. Mass concentrates. Spacetime bends. Escape velocity rises. The event horizon forms. Beyond it, trying harder no longer means what it once meant. The black hole does not defeat effort by being evil or hungry or dramatic. It defeats effort by making effort irrelevant to the global outcome. There is a kind of chill in that, but also a kind of clarity. Sometimes the deepest truths are not loud. They are simply final. And it is worth saying one more time that this finality begins only at the horizon. Before that, action still matters enormously. The difference between crossing and not crossing is everything. If a ship approaching a black hole still remains outside the event horizon, then navigation, planning, orbital mechanics, and engine power may still determine whether the crew survives. There is no need for fatalism too early. Black holes do not instantly devour everything nearby. Their danger is precise, not cartoonish. That precision matters for storytelling too. It keeps the science from becoming melodrama. A black hole is not dangerous because it is infinitely bad at every distance. It is dangerous because once certain thresholds are crossed, the laws become unforgiving in exact ways. That is more interesting than myth. And perhaps more calming too, in a strange sense. The universe may be severe, but it is not arbitrary. The event horizon is not a trapdoor that appears out of nowhere for theatrical effect. It is the natural consequence of mass, geometry, and the speed limit woven into space-time. Once you understand that, the impossibility of escape stops feeling like a statement of cosmic cruelty and begins to feel like a statement of cosmic structure. And structure, even when it is frightening, has a certain peace to it. If you were falling inward and realized the truth, truly realized it, perhaps the most unsettling part would not be panic. Perhaps it would be the quietness of the conclusion. Not, we need more power. Not, we have one last chance. But something more still than that. There is no route left. Not because we failed. Because the world here is made this way. If these slow journeys through physics are helping you unwind, you can gently leave a like, subscribe, or share a comment about which feels stranger to you. That light cannot escape, or that even the most powerful imaginable technology would still fail once the horizon is crossed. For now, let this one idea settle deeply. Outside a black hole, greater effort can still matter. Inside the event horizon, it cannot change the fact that every allowed future leads inward. Trying harder changes the details of the fall, perhaps. It does not change the destination. And in the next part, we move from the logic of inevitability to the experience of it. Because once it becomes clear that effort no longer opens a way out, another question begins to glow in the dark. What would it actually feel like to fall in? Part 7. What falling in would actually feel like. There is a difference between knowing something is inevitable and feeling it happen. Up to this point, we have been building the logic slowly. A star collapses. A black hole forms. Escape velocity rises beyond what even light can manage. The event horizon marks the boundary where all outward futures disappear. And once that boundary is crossed, no engine, no courage, no brilliance, and no amount of power can restore the path back out. That is the logic of the fall. But logic is one thing. Experience is another. And when people imagine black holes, this is often the part that grips them most tightly. Not the equations. Not the diagrams. Not even the event horizon itself. What they really want to know is something more personal, almost whispered rather than asked. What would it actually feel like? Would you know the moment you were too close? Would your body sense the danger before your mind could understand it? Would the universe around you change shape in some obvious way, or would the fall be strangely quiet, almost ordinary, right up until the very end? These questions matter because black holes are not frightening in the way a fire is frightening. Fire gives immediate feedback. Heat rises. Skin recoils. Instinct screams. A black hole, especially a very large one, can be far more deceptive. It can allow a traveler to continue feeling normal long after escape has already become impossible. And that, in a way, is more unnerving than sudden violence. Because there is something deeply human about wanting danger to announce itself. We want edges to look sharp. We want the irreversible moment to feel unmistakable. We want the body to warn us when the future has narrowed. But the universe does not always offer that kindness. So let us imagine the journey slowly. You are falling toward a black hole, not tumbling chaotically, not crashing through debris, but simply falling. Perhaps your ship has failed. Perhaps this is a thought experiment and you are alone in a small capsule. Perhaps there is only a window, a radio that still works for now, and the dark circle ahead of you growing larger as the stars around it bend into strange arcs. At first, if you are still far away, the experience may not feel dramatic at all. This surprises many people. We imagine black holes as if they must feel intense from every distance, as though their very existence should produce some immediate sensory assault. But from far enough away, a black hole behaves gravitationally much like any other object with the same mass. If our sun were replaced, somehow and impossibly, by a black hole of equal mass, Earth would still orbit in almost the same path. The catastrophe for life would come from losing sunlight, not from being suddenly yanked into doom. That is worth remembering. Black holes are not magical vacuum cleaners. Their strangeness becomes overwhelming only when you get close. And as you begin to get closer, the first thing that changes may not be your body at all. It may be your view. The sky around a black hole would not look normal. Light from the stars behind it would curve around the black hole's gravity, creating distortions that feel almost dreamlike. The black hole itself would appear as a dark central region, but around it, the universe would begin to smear, arc, and wrap in ways that do not match ordinary perspective. Parts of the sky behind the black hole could appear above it, below it, or around its edges because the light is being bent along curved paths through spacetime. It would be beautiful in an unsettling way. Not beautiful like a sunset or a forest. Beautiful like a law of nature revealing its full seriousness. The stars would no longer seem fixed in a comfortable dome. The black hole would turn the sky into a lens. Some regions might appear brighter. Some would look stretched. Some would seem doubled or bent into rings. The closer you fall, the more the background universe would distort into a kind of gravitational mirage. And this is an important part of the experience. Because when people ask what falling into a black hole would feel like, they often think only of physical pain or force. But there is also the psychological dimension of watching reality itself stop behaving like the world you know. Imagine looking out your window and seeing the familiar logic of perspective begin to fail. Straight lines no longer feel straight. The stars do not sit where your intuition thinks they should. The black shape ahead is not just dark. It is a darkness that rearranges the entire sky around it. Even before your body feels much, your eyes may understand that you are entering a place where ordinary expectation is no longer reliable. And yet, if the black hole is large enough, your body may still feel strangely calm for a long time. This is where size matters more than people often realize. A smaller black hole, such as a stellar mass black hole formed from the collapse of a massive star, can produce lethal tidal forces well before you even reach the event horizon. We will spend more time with those forces in the next part, because they deserve their own slow treatment. But for now, it is enough to say that the gravity near a smaller black hole changes so rapidly over short distances that the pull on your feet and the pull on your head may become catastrophically different while you are still outside the horizon. A supermassive black hole is different. Because its event horizon is so much larger, the difference in gravity between one part of your body and another at the horizon can be surprisingly mild. If the black hole is enormous enough, you might cross the event horizon without any sharp physical sensation at all. No tearing, no sudden pressure, No jolt announcing the crossing. Just continued falling. This is one of the most haunting facts in the whole story. The line beyond which the universe no longer allows return may feel locally uneventful. You may still be breathing, still thinking, still looking out at the warped light of distant stars, still aware of your hands, your heartbeat, the rhythm of your own thoughts. And all the while, something absolute has already happened. There is no way back. That split, between how calm the body may feel and how severe the physics already is, gives the black hole its particular emotional tone. It is not always a scream. Sometimes it is a realization that arrives quietly and does not leave. If you had instruments with you, they might tell part of the story. They might show the growing strength of the gravitational field. They might track the distortion of background starlight. They might measure time signals from faraway clocks and show that those clocks seem to speed up relative to your own. That part is especially strange, because one of the most extraordinary features of falling toward a black hole is not just what happens to you, but what happens to your relationship with the rest of the universe. According to general relativity, time runs differently in different gravitational conditions. A clock deeper in a gravitational well runs differently from a clock farther away. Near a black hole, this effect becomes enormous. To a distant observer watching you fall, your motions would appear to slow. Your signals would become redder and weaker. You would seem to approach the event horizon more and more gradually, fading toward darkness. But from your point of view, your own clock never misbehaves. Your heartbeat remains your heartbeat. 1 second still feels like 1 second. Your thoughts do not smear or freeze. You do not feel your own time breaking. Instead, what changes is the outside universe. If you could somehow continue seeing and receiving information from far away while you fell, the clocks of the distant universe could appear to speed up relative to yours. Events far away might seem compressed. The future beyond the black hole could begin to rush by, at least in some limited and complicated sense, depending on what exactly you are observing and how the signals reach you. That possibility is almost impossible not to find eerie. Imagine falling inward while the wider universe appears to accelerate. Stars evolving, light shifting, processes far away moving faster than your own private rhythm. It would feel less like traveling through space and more like losing synchronization with reality itself. That may be the most disorienting aspect of the fall. Not pain at first, not motion in the everyday sense, but the gradual realization that your local experience remains calm while your connection to the wider cosmos is being peeled away layer by layer. There is something lonely in that image. At first, radio contact might still work. Messages sent from you could still reach the outside, though with growing difficulty. Messages from outside could still arrive. Perhaps a voice from mission control becomes slower, stranger, more stretched by the relativistic conditions. Perhaps their responses stop making intuitive sense because your time and theirs are no longer aligned in a simple way. Then eventually, even that link approaches its end. The horizon is not a solid curtain dropping in a theatrical instant, but it is still a final separation. Once crossed, no message from you can return to the outside universe. The conversation becomes permanently one-sided. The outside may still imagine, infer, or calculate what happens next, but it will never hear from you again. And still, for you, consciousness could continue for some time. That is worth holding carefully, because it is one of the reasons the event horizon feels so profound. Crossing it is not necessarily the same as immediate destruction. Depending on the size of the black hole, you may continue inward for seconds, minutes, hours, or perhaps longer in your own frame before the deeper regions become fatal. So what would that inward continuation feel like? At first, perhaps, simply like falling. But falling in space is already unlike falling on Earth. On Earth, when you fall, air rushes past you, surfaces approach, impact comes quickly. In orbit or deep space, free fall has a different character. Astronauts in orbit are constantly falling around Earth, but because they and their spacecraft fall together, they feel weightless. This is one of the gentle paradoxes of gravity. In free fall, gravity can feel like its absence. So if you are falling freely toward a black hole, especially before the tidal forces grow strong, you may feel weightless rather than crushed. You would not feel an invisible hand pressing you into the floor. Quite the opposite. You might float in your capsule. Objects beside you might drift. Your body might feel almost normal in the local sense. Again, this defies intuition. We think stronger gravity should feel heavier. But free fall hides gravity in a certain way. What reveals it most dramatically is not the overall pull, but the difference in pull from one location to another. That is where tidal forces come in. They are the part of the black hole that eventually turns quiet inevitability into physical destruction. But before we go there fully, stay a little longer in the strange middle stage. You are falling. You feel weightless. The sky is distorted. The outside universe is slipping out of causal reach. And somewhere behind you, though no sign told you exactly when it happened, the event horizon has already been crossed. Would you know? This is one of the most beautiful and frustrating questions in black hole physics. The honest answer is not always, not directly, and not from local sensation alone, especially for a very large black hole. If your instruments were good enough and your calculations precise enough, you could infer it. You could know intellectually where you were. But the horizon itself is not a wall you crash through. It does not hand you a special sensation to mark the moment. That means the knowledge could arrive in a very human way. Not through pain. Through understanding. You might know because you have done the math and watched the numbers. You might know because the boundary has moved from theory into fact. You might know because every remaining message you try to send outward is now doomed, even if you cannot see that doom happen in real time. And that kind of knowledge has its own emotional texture. It is calmer than panic, but heavier than fear. It is the kind of awareness that settles into the chest and changes the meaning of every second that follows. There is no rescue now. No correction. No return burn. No later moment in which you will wake from a nightmare and realize you never crossed. That kind of certainty, if a mind could bear it clearly, might feel almost sacred in its severity. Not because it is good, but because it is absolute. There is a strange stillness that can come with truths that no longer negotiate. And maybe that is why black holes feel so suitable for slow contemplation. They are not merely violent objects. They are objects that force us to think about finality without noise. Of course, the experience would not remain gentle forever. As you continue inward, the black hole's tidal forces begin to matter more and more. If the black hole is small, they may already have become fatal before the horizon. If it is supermassive, the horizon may have passed almost peacefully, but the deeper fall will not stay that way. The difference in gravitational pull between your feet and your head will grow. The geometry that once felt abstract will become physical. The black hole will stop being just a place that rearranges starlight and starts becoming a place that rearranges matter. But before that happens, there is one more emotional detail worth noticing. A person falling into a black hole does not experience themselves as being suddenly erased from the universe. From their own perspective, they remain a continuing self for a while. Thought follows thought. Breath follows breath. Curiosity may remain alive even in the presence of doom. There is something poignant in that. The mind, a tiny local process made of fragile biological order, continues making sense of things even while moving into a region where no outside witness can follow. The fall becomes private, perhaps more private than any experience can be. And in that privacy, the black hole becomes almost like a final mirror for consciousness. Not a mirror that reflects your face, but one that reflects the limits of your world. It strips away the fantasy that every edge must be negotiable. It leaves you with sensation, thought, and the deepening truth that the path ahead is real whether or not anyone else can ever see it. If these quiet journeys through the universe are helping you drift into rest, You can gently leave a like, subscribe, or share a comment about what feels strangest to you here: the distorted sky, the silence of crossing the horizon, or the idea that you might feel weightless even while falling towards something inescapable. For now, though, let the image remain slow and clear. You are still conscious, still falling, still suspended in your own normal rhythm, even as the wider universe grows stranger around you. The black hole has not shouted. It has not announced your fate with thunder or flame. It has simply taken you into a region where return no longer belongs to the future. And deeper in, waiting with a patience that feels almost inhuman, is the next chapter of the fall. Because after the horizon, and after the quietness, comes the part where gravity stops feeling abstract. The part where the black hole begins to pull differently on different parts of you. The part with the oddly harmless name, and the utterly merciless meaning. Spaghettification. Part 8, Spaghettification and Tidal Forces. There is a moment in almost every deep science story when the language suddenly becomes more vivid than the reality it is trying to describe. Spaghettification is one of those words. It sounds almost playful at first, almost too light for the subject it belongs to. It sounds like something that should not exist in serious physics, like a joke that somehow slipped past the editors and stayed there. And yet the word has survived, partly because it is memorable, and partly because, strange as it sounds, it points towards something very real. If you fall deep enough into a black hole, gravity does not pull on all of you equally. That is the heart of it. And once you understand that, the image behind the word begins to make sense. Up to this point, our journey has been quiet in a very particular way. We have talked about the birth of black holes, about escape velocity, about the event horizon, and about the eerie possibility that falling inward might feel calm for longer than intuition would expect. We have looked out through the window of a falling ship and watched the stars distort. We have followed the logic of why no engine can bring you back once the horizon is crossed. But there is another side to black holes, one that is not only about logic, but about the body. Not because black holes suddenly become angry. Not because the universe becomes theatrical. But because gravity, when it changes fast enough across a short distance, stops being a gentle background fact and becomes a tearing geometry. That tearing geometry is what tidal forces are. And to understand them, it helps to begin very far from black holes, somewhere softer and more familiar. The tides on Earth. Every day, the oceans rise and fall under the influence of the moon, and to a lesser extent, the sun. That alone is already a subtle reminder that gravity is not just about whether something is strong or weak. It is also about difference. The side of Earth facing the moon feels the moon's pull a little more strongly than the center of Earth does. And the center feels it a little more strongly than the far side. Those tiny differences stretch the planet slightly and help create the motion of the seas. So the tides are not caused simply by gravity. They are caused by uneven gravity. That unevenness is the key. If gravity acted on every part of Earth in exactly the same way, there would be no tidal effect. The whole planet would just move together. But because one side is pulled a little harder than another, Earth is very gently stretched. The oceans respond. The coastlines feel it. The tide comes in, and the tide goes out. It is a quiet example of something much deeper. Tidal forces are what happen when gravity changes over distance. On Earth, they are gentle enough to move oceans. Near a black hole, they can move bodies, bones, atoms, and eventually the very structure of matter itself. That is the same principle taken to an unimaginable extreme. If you were floating freely in deep space far from any strong source of gravity, your feet and your head would be in almost the same gravitational environment. Every part of your body would be moving along together. There would be no important difference between one end of you and the other. But as you approach a compact massive object, that begins to change. The part of your body closer to the object feels a stronger pull than the part farther away. If you are falling feet first toward a black hole, your feet are slightly closer to the center than your head is. That sounds like a small detail, and at first it is. But gravity changes very rapidly near a black hole, especially a small one. So that little difference in distance becomes a huge difference in pull. Your feet are pulled more strongly than your knees more strongly than your waist more strongly than your chest more strongly than your head. At the same time, the left and right sides of your body are being pulled inward toward the center as well, so you are not only stretched from top to bottom, you are also compressed from side to side. That is what the black hole does to shape. It stretches you along the direction of the fall and squeezes you across the other directions. Longer, thinner, narrower. That is the origin of the famous word. Not because the universe has a sense of humor, but because the comparison is disturbingly apt. And yet, even here, it helps to stay calm and precise. Spaghettification is not a mysterious extra feature of black holes. It is not some separate force waiting in ambush. It is just tidal gravity made severe. It is the natural consequence of falling into a place where the gravitational field changes dramatically across the size of a human body. That matters because it keeps the story honest. Black holes are strange enough without turning them into myth. This is physics, not fantasy. And because it is physics, the details become even more interesting than the dramatic version people often carry around in their heads. For example, one of the most important things about spaghettification is this. It does not happen at the same place for every black hole. That surprises many people the first time they hear it. There is a tendency to imagine that the event horizon and the lethal stretching are basically the same thing, as though crossing the horizon means instant destruction. But that is not always true. In fact, whether you are torn apart before or after crossing the event horizon depends strongly on the size of the black hole. A smaller black hole is, in some ways, more violent near the horizon. A supermassive black hole can be gentler there. That sounds backward, but it is not. A supermassive black hole has much more mass, yes, but it also has a much larger event horizon. Its horizon lies much farther from the center. And because tidal forces depend on how fast gravity changes over distance, not just on how strong gravity is in some general sense, the stretching at the horizon of a supermassive black hole can be relatively mild. A stellar mass black hole is different. Its event horizon is much closer to the center, packed into a smaller region. The gradient in gravity near that horizon can be so steep that the tidal forces become fatal before you even get there. So there are black holes for which the event horizon is not the first truly dangerous threshold. The damage begins outside. And there are black holes for which you could, at least in principle, cross the horizon intact and only later meet the full force of tidal destruction as you continue inward. This difference is one of the most hauntingly elegant details in black hole physics. The same law, the same kind of object, very different local experience. If you fell toward a small stellar mass black hole, the warning might come early and brutally. Long before the horizon, your body would begin to feel the unequal pull. At first perhaps just tension, then something much worse. The pull on your feet would become meaningfully stronger than the pull on your head. The structure of your body, held together by muscles, bones, tissues, and chemical bonds, would not be able to remain as it is. The black hole would not need to touch you. It would not need a surface. The difference in gravity alone would be enough. You would be stretched, then torn. And not all at once in the way explosions work, but through the relentless logic of differential force. The body is built to handle many things. It can withstand acceleration, pressure, cold, heat, and injury up to a point. But it is not built to remain intact when different parts of it are being asked to follow radically different gravitational instructions. That is what tidal forces are, in the most human sense. Conflicting instructions written into the body at the same time. Downward faster here. Downward slower there. Inward from the sides. Elongation along the fall. compression across it. And because black holes are patient, the process is not about drama. It is about inevitability. A supermassive black hole tells a stranger story. At first, your body might feel fine. That is not an exaggeration. At the horizon of an enormous black hole, the difference between the pull on your head and your feet could be so small that you would notice nothing unusual in a bodily sense. You would drift across the event horizon as if crossing an invisible line in open space. No alarm, no tearing, no pain to announce the moment. The danger would still be total in the large-scale sense, because return is no longer possible, but the local experience could remain calm. That is why part of the black hole story feels almost unfair to intuition. The most final boundary may not hurt. The hurting comes later. Deeper in. As you continue falling inward, the black hole's gravitational field becomes more extreme. The difference in pull between nearby points grows and grows. What was once negligible becomes noticeable, then powerful, then overwhelming. At some depth, even in a supermassive black hole, the tidal forces begin to take command of the body. First perhaps in ways too subtle to name clearly, then in ways that would no longer be ignorable. It is hard to speak about this without becoming either too cold or too graphic, and neither tone is right for where we are. So let us keep it gentle and truthful. Your body is an arrangement of structure. Bones give support. Tissues connect. Organs hold form. Nerves carry signals. Cells maintain boundaries. Molecules keep their places because the forces between them remain stronger than the stresses trying to pull them apart. Tidal forces begin undoing that order from the scale of the body downward. What was once held together begins to be asked to move at slightly different rates, then more different rates, then impossibly different rates. The body can survive small differences. It can even survive large ones for brief moments under certain conditions. But eventually the gradient becomes too severe. The body no longer behaves as a body. It becomes matter following the black hole's geometry. That is one of the deeper truths hidden inside the vivid nickname. Spaghettification is not really about flesh in any special sense. It is about the loss of ordinary structure under extreme tidal stress. A spacecraft could be stretched. A rock could be stretched. A stream of gas could be stretched. A star passing too close to a black hole can be torn apart in what astronomers call a tidal disruption event, producing extraordinary flashes of light as the shredded stellar material spirals around the black hole. So this is not just a human story. It is a story about what black holes do to organized matter. They take shape and place it under a gradient too severe to preserve it. This is part of why black holes remain so important in astrophysics. They are not only endpoints of collapse. They are laboratories of extreme gravity. Around them, stars can be ripped apart. Disks of matter can heat to incredible temperatures. Jets can be launched near light speed. Time and light are distorted. Space and structure are tested close to their limits. And in the middle of all that, the simplest human version of the story remains hauntingly clear. If you fall deep enough, gravity stops feeling like falling and starts feeling like being taken apart by the difference between one place and another. That difference is everything. It is also worth noticing that the word stretching can be misleading if imagined too slowly or too neatly. We might picture an almost cartoon-like lengthening, as though a person simply becomes thinner and taller in a smooth, continuous way. Reality would be more severe than that. The body would not politely reshape itself into a longer version. Biological structure fails long before that kind of image could remain tidy. The nickname helps the imagination, but the underlying process is far more destructive than the word sounds. Even so, the nickname survives because it captures the direction of the distortion. Longitudinal stretching, lateral squeezing, that much is true. And because it is true, it gives us one of the clearest windows into how black holes differ from almost every danger we know on Earth. Earthly dangers often involve impact, combustion, chemistry, disease, or pressure. The black hole's signature violence is geometry. It is the violence of a world in which the force field changes too much across too little space. That is a cold sentence, perhaps, but also a beautiful one in its own way. Black holes reveal how much of reality depends on gradients, not just magnitudes. A thing can be intense and still survivable if it is uniform. A thing can be moderate and devastating if it changes sharply enough across your own size. That is true in physics more broadly too. Storm winds become dangerous not only because they are strong, but because the wind can differ from one place to another. Pressure differences drive motion. Temperature differences drive flow. Tidal differences raise oceans. Black holes take that general principle and push it into a region where ordinary matter loses the argument completely. If you are listening closely, you may notice that all of this makes the black hole feel less like a hungry object and more like a place where the rules of staying whole no longer cooperate. That is a more accurate feeling. The black hole does not attack in the way an animal attacks. It does not choose a victim. It simply sets the conditions under which intact structure becomes impossible. And there is something quietly terrifying about that impersonality. The universe does not need intention to be absolute. A law is enough. At this point, another question sometimes appears. Would you feel pain? The honest answer is that beyond a certain point, the body would be under such extreme stress that ordinary categories of sensation stop being reliable guides. The process is not something a nervous system is built to represent meaningfully for very long. What matters more for our understanding is the mechanism. Tidal forces rise. Structural integrity fails. The body ceases to remain a coherent human body. For a sleep-oriented telling like this, that is enough. The science matters more than the gore. And the science already says something profound. Black holes do not merely prevent escape. They eventually erase the physical conditions that allow a body to remain a body. That gives the journey a second kind of finality. The event horizon is the end of return. Spaghettification is the end of structure. And in between those two endings, there may be a span of time, especially in a supermassive black hole, where consciousness continues while both truths slowly approach each other. That is an extraordinary thought. A person could cross the horizon intact and still have moments later in which the body remains whole, the mind remains active, and the sky, however distorted, is still visible through the window. The horizon does not instantly destroy. It commits the future. The destruction comes deeper in, when the gradient rises beyond what matter can survive. That distinction matters because it gives the black hole interior a shape. It is not just a single instant of doom. It is a sequence. First the loss of escape, then the continuation of the fall, then, deeper in, the failure of structure. And somewhere beyond that lies the question we still cannot fully answer. What happens at the singularity itself? General relativity suggests a region where curvature becomes infinite and the known laws of physics break down. But that is still partly hidden from us behind the fact that no signal can come back. The black hole keeps its deepest secret. Perhaps that is why tidal forces feel so important in the story. They are among the last things we can still describe with some clarity before the physics becomes fully obscure. We understand gradients. We understand stress. We understand why stretching and squeezing must intensify. In that sense, spaghettification is one of the final readable chapters before the book turns opaque. And it is a reminder that the black hole is not just a symbol of mystery. It is also an object with brutally concrete consequences. Bodies are not exempt. Stars are not exempt. Matter is not exempt. Get close enough, and the black hole translates geometry into destruction. If these slow explorations of the universe are helping you rest, you can gently leave a like, subscribe, or share in the comments which detail feels strangest here. That tides on Earth and the tearing near a black hole come from the same basic principle. or that a supermassive black hole might let you cross the horizon intact before the real physical damage begins. For now, let the image stay quiet. You are still falling. At first, nothing dramatic. Then deeper in, the differences begin. Your feet are asked to fall faster than your head. Your sides are pressed inward. Your shape is no longer simply yours. The black hole is no longer only bending light and time around you. It is beginning to bend your body into its own severe language. And yet, even here, one last strange question remains. If black holes seal things in so completely, is that truly the whole story? Or does the universe, in some subtle and unexpected way, allow anything at all to escape after all? Part 9. Can anything ever escape at all? By this point in the journey, the black hole can feel almost completely sealed. A star collapsed. Gravity won. The event horizon formed. Light could no longer return. The body, if it fell deep enough, would eventually be stretched and broken apart by tidal forces. Every path inward became final. Every outward future disappeared. So it is only natural that another question begins to rise. Is that really the end of the story? Is a black hole truly perfect in its silence, perfect in its darkness, perfect in its refusal to give anything back? Or is there, somewhere in all of this, even the faintest kind of leak? That question matters because black holes feel so absolute that the mind almost wants to test them. We want to know whether there is any exception hiding in the machinery, any crack in the logic, any small and strange way the universe softens the rule. And here, unexpectedly, the answer becomes more subtle. Because according to modern physics, a black hole is not completely mute forever. Something can come from it. But what comes from it is not what most people imagine. It is not a person climbing back out. It is not a beam of trapped starlight finally finding a route home. It is not a spaceship emerging from the darkness after a long and impossible detour. It is something much stranger than that. To get there, we need to move carefully, because this is one of those places where black hole science often gets oversimplified into something misleading. People hear one phrase, black holes evaporate, or black holes emit radiation, and the mind jumps too quickly. It starts imagining the black hole as if it were slowly spitting things back out, as if whatever fell in might eventually reappear in another form, like a cosmic recycling process with a very long delay. But that is not really the right picture. So let us slow it down. Let us begin with the older intuition first. In Einstein's general relativity alone, a black hole is almost perfectly one way. Matter can go in. Light can go in. Information, at least in the ordinary sense, seems to go in. The event horizon closes the story from the outside. If you were describing a black hole using only that classical picture, it would feel nearly eternal and completely dark. And for a while, that is more or less how physicists thought about them. Then, in the 1970s, something remarkable happened. Stephen Hawking, working with ideas from quantum theory and gravity, found that black holes are not entirely black after all. That sentence changed everything. Not because it made escape easy. Not because it rescued anyone who had fallen in. But because it revealed that the boundary around a black hole is stranger than anyone had fully realized. To understand the basic idea, it helps to step away from the black hole for just a moment and look at empty space itself. Because one of the great surprises of quantum physics is that what we casually call empty space is not really empty in the simple everyday sense. It is not a perfectly blank stage with nothing happening. Instead, at very tiny scales, quantum fields remain active even in what we would think of as vacuum. Fluctuations occur. The emptiness is restless in a way ordinary intuition would never guess. People sometimes describe this by saying that pairs of particles and antiparticles briefly appear and then disappear again. Now, this picture is a simplification, and physicists can be careful about how literally to take it. But as a gentle mental image, it is useful. Space is not dead silence. It has a kind of fine-grained shimmer to it, a restless background activity built into the quantum world. Near the event horizon of a black hole, that shimmer takes on a new importance. Very loosely speaking, the presence of the horizon changes how these quantum processes play out. The black hole's gravitational environment allows energy to be carried away in the form of radiation detectable to the outside universe. To a distant observer, the black hole behaves as though it has a temperature and emits a very faint glow. That glow is what we call Hawking radiation. And once you hear that, a black hole changes character just a little. It is still dark in the ordinary sense. It is still inescapable from within. It is still one of the most severe objects in the universe. But it is no longer a perfect prison with no outward consequence at all. Over unimaginably long periods of time, it can lose energy. It can slowly shrink. It can, in principle, evaporate. That is the subtle leak. And yet, it is very important not to misunderstand what that means. Hawking radiation does not mean that things which fell in are climbing back out. It does not mean that if a spaceship crosses the event horizon, its atoms will eventually come streaming back into the universe in a recognizable way. It does not mean the black hole is opening a tiny door and releasing its contents. The radiation comes from the quantum behavior of fields in the black hole's curved spacetime environment, especially near the horizon. It is not a classical return of whatever entered. It is new outgoing radiation associated with the black hole's existence as a quantum object. That distinction is everything. Because the title of our journey is about escaping a black hole. And in that sense, the rule still holds with full severity. Once something is inside the event horizon, it does not turn around and come back out in any ordinary physical way. No ladder lowers. No hidden tunnel opens. No personal rescue is smuggled through the equations. What Hawking radiation tells us is not that the trapped thing escapes. It tells us that black holes themselves are not perfectly eternal when quantum theory is taken seriously. That is much stranger, and much colder. Imagine a locked room built so perfectly that nothing inside can leave through the door. Then imagine learning that the room itself, over billions upon billions of years, slowly loses a little of its structure to the outside world, not by opening the door, but by participating in deeper laws of reality. The room is not releasing the prisoner in any ordinary sense. The room itself is fading. That is closer to the truth. And when I say long timescales, I mean truly long. For black holes formed from stars, the evaporation time is vastly longer than the current age of the universe. For supermassive black holes, the timescales are so enormous that ordinary language almost stops helping. Trillions of years is not even close. We are talking about durations so extreme that the stars themselves will be long gone, galaxies transformed, ordinary cosmic life extinguished, before such black holes truly evaporate in full. So Hawking radiation is real in the theoretical picture, but it is not dramatic in the way popular imagination sometimes wants it to be. A black hole is not hissing loudly into space like a furnace. Large black holes are extraordinarily cold in this sense. In fact, the bigger the black hole, the colder it is. That is one of the most counterintuitive details in the whole subject. A small black hole emits more strongly. A large black hole emits less strongly. That feels backward because we are used to larger things seeming more powerful. But in Hawking's result, temperature and size work against that intuition. Supermassive black holes are colder than the cosmic microwave background that fills the universe today. In practical terms, they are absorbing more surrounding energy than they are losing through Hawking radiation, at least in the current era of the universe. So even the leak is patient. The black hole gives nothing back in any humanly meaningful span of time. And still, the existence of Hawking radiation matters enormously, because it tells us that the black hole is not merely a gravitational object. It is also a thermodynamic one. It has temperature. It has entropy. It participates in the deep relationship between gravity, quantum theory, and information. And that is where the story becomes even more mysterious. Because once Hawking showed that black holes can radiate, another question appeared, and it has troubled physics ever since. What happens to the information about what fell in? This is one of the deepest puzzles in modern theoretical physics. Not information in the casual sense of data on a hard drive or memories in a notebook, though those are included in principle. Information here means the complete physical description of what something is, how it is arranged, what state it occupies. In standard quantum mechanics, information is not supposed to be truly destroyed. The detailed evolution of a system may become unimaginably scrambled, but the underlying information should still exist in some form. Black holes seem to challenge that. If a black hole forms, swallows matter, and later evaporates into what appears to be featureless thermal radiation, then where did the information go? Was it destroyed? Hidden? Encoded somehow in subtle correlations within the radiation? Preserved on the horizon in ways we do not yet fully understand? This is what people mean when they talk about the black hole information paradox. And it is not some trivial academic footnote. It is one of the places where our two deepest descriptions of nature, general relativity and quantum mechanics, press hardest against each other. General relativity gives us the event horizon, the inward fall, the classical seal. Quantum theory gives us Hawking radiation and the refusal to casually destroy information. Put them together, and the universe begins asking a question we still cannot answer in complete and comfortable detail. That alone is worth pausing with. Even after all these years, even after all the equations, telescopes, and thought experiments, black holes remain unfinished territory for the human mind. We understand them well enough to say that escape from inside is impossible in the ordinary sense. We understand them well enough to predict horizons, mergers, tidal forces, and gravitational waves. We understand enough to image their shadows and track their influence on stars and galaxies. And still, at the deepest level, they keep one of their central secrets. That gives part 9 a slightly different emotional tone from the earlier parts. Earlier, the black hole felt closed and severe in a clean way. Here, it becomes severe and mysterious at the same time. It is still a prison, still a one-way geometry. But now the prison itself participates in quantum uncertainty. It glows faintly. It changes over vast time. It raises questions about whether information is truly lost or merely hidden in ways our current understanding only partly grasps. So, can anything ever escape at all? If by anything, we mean a person, a signal, a beam of light, a spaceship, or any recognizable object that has crossed the event horizon, then no. The answer remains no. That part of the story has not been softened. If by anything, we mean can a black hole, as a quantum object, slowly emit radiation to the outside universe and lose energy over inconceivably long timescales, then yes. In that limited and very important sense, a black hole is not perfectly closed forever. And the difference between those two yes or no answers is the whole point. Because one speaks to escape, the other speaks to evaporation. One is about what happens to you if you fall in. The other is about what happens to the black hole across times longer than most of the universe's familiar structures can survive. Those are not the same story. It is also worth noticing that Hawking radiation does not make the black hole less strange. It makes it more strange. A purely classical black hole is severe, but conceptually tidy. Things go in, nothing comes out. End of story. Hawking radiation ruins that tidiness in the most beautiful way. It says, not so fast. The universe at small scales is restless. Horizons are not as mute as they appear. Gravity and quantum theory, when allowed to meet, produce a faint whisper where we once imagined only silence. That whisper is not rescue, but it is revelation. And perhaps that is why black holes have kept such a hold on both scientists and ordinary listeners. They are not just scary or impressive, they are intellectually alive. Every time we think we have reduced them to a clean dramatic slogan, they reveal another layer. First they are dark, then not completely dark. First they trap everything, then they evaporate. First they seem to destroy information, then perhaps they do not. First they look like the endpoint of gravity, then they begin to look like clues toward a deeper theory of the universe itself. In that sense, black holes are not only places where things disappear, they are also places where questions become sharper. And there is one more subtle thought worth adding before we leave this part behind. If a black hole eventually evaporates completely, then whatever once fell into it is still not simply recovered in the ordinary emotional way we might wish. The person who crossed the event horizon is not waiting somewhere to be unpacked by late-time radiation. The recognizable structure is gone. The local story inside the horizon still ends inward. Hawking radiation does not undo the one-way nature of the fall for the thing that fell. That is a hard sentence, but an important one. Because otherwise the imagination starts to cheat. It starts to whisper, maybe nothing is ever really lost, maybe the black hole gives it all back eventually, maybe escape just takes longer than we thought. But the physics does not really support that comforting version. Whatever deeper truth about information ultimately emerges, it will not turn the black hole into an ordinary reversible door. It will not make falling in the same as taking a very long detour. The event horizon remains the end of escape in any human, practical, or narrative sense. And yet, the black hole also refuses to be completely inert. It radiates. It ages. It may vanish in the end. There is something almost melancholy in that. The universe's darkest objects are not permanent monuments. Even they, given enough time, participate in change. Even they are not outside the law that nothing material arrangement lasts forever in the same form. A black hole can outlive stars, galaxies, civilizations, and worlds. But perhaps not eternity. That is a beautiful thought to carry into the final part. Because if the black hole is not merely a prison but also a clue, then the question becomes larger than escape alone. It becomes a question about what black holes teach us regarding the shape of reality itself. About time, finality, information, and the meaning of impossible. If these slow explorations help you settle into rest, you can gently leave a like, subscribe, or share a comment about which black hole idea feels most surprising to you now. That black holes may radiate, that bigger ones are actually colder, or that the deepest puzzle may be about information rather than gravity alone. For now, let this quiet distinction remain clear. Nothing that crosses the event horizon escapes in the ordinary sense. But the black hole itself is not perfectly silent forever. It may whisper. It may fade. It may slowly surrender energy to the universe across stretches of time so vast they barely fit inside thought. And that leaves us with one final step. Because after all the falling, the horizons, the stretched light, the tidal forces, and even the strange faint glow of Hawking radiation, one question remains. What, in the end, is a black hole really telling us about the universe? Not just about danger. Not just about gravity. But about the meaning of a place where, out, no longer exists. Part 10. Why a black hole changes the meaning of impossible. There are many things in life we casually call impossible. Sometimes we mean unlikely. Sometimes we mean difficult. Sometimes we mean beyond our current technology, beyond our current budget, beyond our current lifespan, or simply beyond the patience we are willing to spend. A person says it is impossible to climb a certain mountain, and then someone else climbs it. A generation says it is impossible to fly, and then the sky fills with aircraft. People say it is impossible to walk on the moon, to photograph a black hole, to hear the collision of dead stars in another galaxy, and then, slowly, over time, the impossible becomes history. So we grow up with a certain lesson. Impossible is often temporary. Impossible is often just another word for not yet. That lesson is powerful. In many areas of life, it is even wise. It teaches effort. It teaches curiosity. It teaches humility before the future. It reminds us that reality is often larger than current imagination. But then black holes arrive. And black holes ask us to be more precise. Because escaping a black hole is not impossible in the way early flight once seemed impossible. It is not impossible in the way crossing an ocean once seemed impossible. It is not impossible in the way building better engines, better materials, or better mathematics once seemed impossible. It is impossible in a much colder way. It is impossible because, beyond the event horizon, the universe no longer offers out as a future. And that changes the emotional meaning of the word. All through this journey, we have been moving toward that realization from different angles. We began with a star, bright and ordinary in appearance, living out its long internal struggle between gravity and pressure. We watched it run out of options, collapse, and become something so compact that spacetime itself was forced into a new and extreme geometry. We followed the logic of escape velocity until it rose beyond the speed of light. We arrived at the event horizon, that invisible line where return disappears. We looked through the eyes of the falling traveler and saw how quiet the crossing could be. We felt the body entering the realm of tidal forces, where structure itself begins to fail. We even allowed quantum theory to complicate the picture, whispering that black holes may radiate faintly across inconceivable spans of time. And after all of that, the deepest lesson remains strangely simple. A black hole is not just a dangerous object. It is a place where the ordinary human faith in alternatives runs out. That may be why black holes continue to feel so profound even to people who do not spend their lives with equations. They are not only astrophysical objects. They are revelations about the architecture of limits. Most limits in life are negotiable. A locked door can be opened. A difficult road can be paved. A dangerous environment can be survived with better preparation. But black holes reveal a different category of boundary. A boundary that does not care how clever you are, how brave you are, how advanced you are, or how deeply you believe in second chances. There is a point beyond which the universe simply stops including escape in the list of allowed stories. And perhaps that is why the black hole does not feel merely frightening. It feels final. Not the finality of a slammed door, but the finality of a law. There is a strange dignity in that distinction. A door suggests intention. A law does not. The black hole is not hostile. It does not trap out of malice. It does not punish, choose, or resent. It simply exists in a state where geometry has become one-directional. Once you cross the horizon, you are not being held by force in the ordinary dramatic sense. You are being carried by the shape of spacetime into a future that only goes inward. And that word inward becomes very important here. Because on Earth, inward and outward feel like simple directions. Inward means toward the center of something. Outward means away. We imagine them as mirror choices, like left and right, forward and back. But inside a black hole, inward becomes more than a direction. It becomes destiny in the physical sense. That is one of the reasons the black hole changes the meaning of impossible. Usually, when we say something is impossible, we imagine a challenge standing in the way, a mountain too high, a force too strong, a lack of fuel, a lack of time, a lack of knowledge. There is still a world beyond the obstacle. We just cannot reach it. A black hole is different. The obstacle is not standing between you and freedom. Freedom itself has ceased to be part of the geometry. That is not just harder. That is deeper. And when you let that settle for a moment, the black hole begins to feel less like a cosmic trap and more like a philosophical lesson written in gravity. It tells us that the universe has different kinds of no. Some no's are invitations to innovate. Some no's are invitations to wait. Some no's are invitations to grow. And some no's are not invitations at all. They are descriptions. The event horizon is one of those descriptions. Beyond this line, return is no longer a meaningful possibility. It is such a simple sentence, but it reaches very far. It reaches into our understanding of time. It reaches into our understanding of causality. It reaches into our understanding of observation itself, because once light cannot get out, the outside universe loses direct access to what happens within. It even reaches into our understanding of knowledge. There are places, the black hole reminds us, where not only can we not go, but where information itself cannot come back in the ordinary way. That is one of the quietest and most unnerving truths in all of science. The universe contains regions that are not merely dangerous to enter. They are informationally sealed. That phrase may sound technical, but it carries an emotional weight. It means that a black hole is not only a place where matter falls inward. It is a place where storytelling ends from the outside. After the event horizon, the universe cannot simply watch and report back. The interior continues, but the report fails. The witness fails. Light fails. And in a cosmos where light is our primary messenger, that failure feels almost sacred in its severity. We are creatures who know the world mostly through things escaping from it. Light escapes stars. Sound escapes mouths. Signals escape satellites. Meaning escapes into language. A black hole is one of the rare places where escape itself is systematically denied. That is why it does not just challenge engineering. It challenges intuition. And perhaps that is the deepest reason black holes remain so compelling. They do not merely sit at the edge of astronomy. They sit at the edge of what our minds are naturally good at imagining. The human brain evolved in a world of hills, rivers, trees, weather, faces, and falling objects. It did not evolve to understand horizons that are not surfaces, time that runs differently in different places, or regions where all possible futures point toward one invisible center. And yet, somehow, through mathematics, thought experiments, and patient observation, we have learned to see some part of this truth anyway. That alone is worth pausing with. A creature from a small rocky planet, orbiting an ordinary star in one spiral galaxy among billions, has learned enough to describe a place from which even light cannot return. That is a remarkable thing. The black hole changes the meaning of impossible, yes, but it also changes the meaning of understanding. Because even though no one can return from inside to give a report, the human mind has still reached astonishingly close to the edge through theory and evidence. We have watched stars orbit invisible masses. We have heard black holes collide through gravitational waves. We have imaged the shadows of their horizons. We have traced their influence in galaxies across the deep sky. We have found ways to know something real about places we can never visit safely. So black holes do not only teach humility, they also teach the power of patient reasoning. There is something comforting in that, perhaps especially at night. The universe is vast, severe, and often indifferent to our wishes, but it is not entirely closed to our curiosity. Even its darkest objects leave traces. Even their silence has structure. Even their secrecy can be approached. Not solved completely, perhaps. Not yet, but approached. And still, for all that science gives us, a black hole keeps one crucial emotional truth intact. It reminds us that not every frontier is meant to be crossed and returned from. Some frontiers are boundaries in a stronger sense. Not because the universe is cruel, but because reality is not obligated to preserve reversibility everywhere. That idea becomes even more interesting when placed next to the older human love of exploration. For centuries, the unknown has called to us in the same way. Oceans, poles, deserts, the deep sky, the interior of the atom. Again and again, the pattern has been the same. Something seems unreachable. Human beings go anyway. They map, build, adapt, and eventually return with stories. Black holes interrupt that narrative. They are among the very few places where the old heroic rhythm breaks. There can be a journey in. There cannot be a journey back. And that matters, not because it destroys wonder, but because it purifies wonder into something more serious. The black hole is not another continent waiting to be charted by brave travelers. It is a limit case of reality itself. It is the place where exploration becomes asymmetrical, where inquiry can still reach through theory and observation, but where physical return is no longer part of the bargain. That gives black holes a tone unlike almost anything else in the cosmos. Nebulae are beautiful. Galaxies are grand. Supernovae are violent. But black holes feel absolute. They take familiar things, mass, light, time, distance, and push them until familiar language begins to fail. Even the words we use around them start becoming philosophical almost against our will. Horizon, singularity, information, escape, return, impossible. And maybe that is because black holes are not only objects in the universe, they are also mirrors held up to the limits of human categories. We like to divide things into can and cannot, but black holes force us to refine that. Can, if enough energy is available. Can, if technology improves. Can, if time is given. Cannot, because the structure of reality forbids it. That last category is rarer, and black holes belong there. There is something almost calming in being forced to distinguish those different meanings carefully. It reminds us that reality is not vague. It may be strange, but it is not vague. The line between hard and impossible is not always arbitrary. Sometimes the universe draws it with extraordinary sharpness. And nowhere is that sharper than the event horizon. Outside it, the black hole is still a gravitational object one can orbit, study, avoid, or perhaps approach with care. At it, the meaning of escape reaches its limit. Inside it, impossible stops being dramatic language and becomes geometry. That is the transformation this whole story has been leading us toward. The black hole changes the meaning of impossible by removing the last hidden hope that maybe enough effort could still create another route. There is no secret route. There is no deeper level of trying. There is no heroic final burst that restores the outward future. And perhaps this is where the story becomes unexpectedly human again. Because although black holes are cosmic objects, the lesson they bring touches something in us beyond physics. We spend so much of our lives believing, often rightly, that persistence can bend outcomes. That if we keep working, keep thinking, keep building, keep enduring, we may yet find a way through. Usually that belief is worth protecting. But there is also wisdom in knowing that reality has edges. Not all edges are failures. Some are definitions. The horizon of a black hole is like that. It does not mock effort. It simply marks the point where effort no longer operates in the old category. And that, strangely enough, can make the black hole feel less like a monster and more like a truth. A severe truth, yes, but a truth. Even Hawking radiation, which seemed at first to soften the black hole's finality, does not really undo this lesson. It adds nuance, not mercy. It tells us that black holes participate in quantum physics, that they glow faintly, that they may evaporate over unimaginable timescales. But it does not turn the black hole into a revolving door. It does not rescue what has fallen in. It does not restore the old story of departure and return. Instead, it makes the black hole even more profound. Not only is escape impossible from within, but the object itself becomes a clue that our deepest theories, gravity and quantum mechanics, still do not fit together perfectly. The black hole is both a prison and a question, a boundary and a hint, a finality and an unfinished puzzle. That is an extraordinary combination. It means the black hole does not merely end stories. It opens deeper ones. And maybe that is the best place to arrive after such a long and careful fall. Not at fear, but at awe. Not the loud awe of explosions and spectacle, but the quieter kind. The kind that comes when you realize that the universe contains objects so severe that they force language itself to become more honest. A black hole teaches that impossible does not always mean not yet. Sometimes it means something much more exact. It means there is no path from here to there that the universe allows. And that is enough. If you imagine again the astronaut from the very beginning, drifting toward the perfect circle of darkness, you can now feel how much richer the scene has become. At first, it was simply frightening. A human being approaching something inescapable. But now, after all these parts, the meaning has changed. The astronaut is not just falling into danger. They are falling into a place where space and time themselves have become one way. They are approaching a boundary that is invisible but absolute. They are entering a region where light cannot report back, where the outside universe loses contact, where effort cannot restore choice, where the body may remain calm for a while even after return has already vanished, where tidal forces eventually translate geometry into destruction, and where even the final darkness may still whisper quantum secrets across impossible expanses of time. That is no longer just fear. That is one of the most profound stories modern science can tell. And perhaps that is why it makes such good company for sleepless nights. Not because black holes are comforting in any ordinary sense, but because they place our restless minds inside a larger frame. They remind us that the universe is stranger than worry, larger than routine, and deeper than the little loops of thought we often get trapped in after dark. A black hole is terrifying, yes, but it is also clarifying. It shows that some truths are not negotiable. It shows that some mysteries do not need to be solved completely in order to be real. And it shows that the universe, even in its most severe forms, can still be approached with patience, humility, and wonder. If these slow journeys through the universe have helped you unwind, you can gently leave a like, subscribe, or share in the comments which idea stayed with you most: the event horizon, the silence of light failing to escape, the strange calm of crossing into no return, or the deeper thought that a black hole changes what impossible really means. And for now, let the story come to rest here. A black hole is not merely a place where things are trapped. It is a place where the universe reveals one of its hardest boundaries. Not because it wants to frighten us, but because reality, at its most extreme, is capable of drawing lines that no will, no speed, and no brilliance can cross backward. That is why escaping a black hole is truly impossible. Not because the prison is strong, but because beyond the horizon, the road called out is gone. And somewhere in that perfect darkness, where light itself fails and time bends inward, the universe keeps one of its deepest lessons waiting in silence. Some impossibilities are challenges, and some impossibilities are truths.